So we're going to start with a high-level intro to network security protocols. We're not going to go into too much detail in this first section here. It'll just provide a higher level landscape for us before we go down into SSL and TLS. So as you know, there's a lot of different security protocols out there today, and which protocol you choose depends on your applications and your use case. But there are some common ones that tend to come up more frequently than others. Some of those are SSL and TLS, SSH, IPsec, VPN, and Kerberos. So starting with SSL TLS, this is secure socket layer and transport layer security. It sits between the application and transport layers and provides essentially security for a single connection, which is going to differ from some of the other protocols out there. Because it's doing a single connection, security for that single connection, you have per connection settings that you can customize by your application or at build time. TLS uses X509 certificates or pre-shared keys for peer authentication. You can authenticate one or both sides of the connection. TCP/IP is the most common transport layer used underneath TLS, but that really can vary, again, depending on application. The next protocol is SSH, which stands for Secure Shell. This provides a secure tunnel between a client and server, and it's composed of channels internally. It's commonly used for remote shell access. You've probably all SSH'd into a server box, maybe run some remote commands or done a file transfer with SFTP or SCP. IPsec is similar to TLS, has the same higher level goals of confidentiality, integrity, and authentication, but it's going to operate at a lower level in the network stack, down at layer 3 in the OSI model. It was originally developed in 1998 and updated in 2005. It's defined in RFC numbered 4301. It works with something called IKE, which is the Internet Key Exchange. So you can see on the little diagram on the left here showing you, SSL and TLS is more up at the session above the transport layer, whereas IPsec is down kind of at the network level. It can either be integrated, where it's inside of the stack itself, or it can be above what they call a bump in the stack, or bits, where it's inserted in between two layers. So every once in a while we get asked, the differences between TLS and IPsec. They both fulfill the same high-level goals. The major difference is where they sit in the stack. Using SSL and TLS, you can take advantage of TCP's built-in robustness since we're sitting on top of TCP. Your applications can select when they want security, what kind of security they want, and have kind of fine-grained control per connection. TLS compared to IPsec is less resource intensive since it's got a smaller footprint. And then if you look at IPsec, since this is lower, all the applications on top of it inherently get the benefits of security. But because of that, you're not getting the per connection control or tuning that you may want. It's a little more complex than SSL since it has to make up for the lack of TCP robustness underneath it. And obviously, with its more robustness and a little bit larger size, it's going to be less friendly or easy, harder to put down into a low resource device than TLS. The next technology here is a VPN, virtual private network. It provides a private network connection over a public one. There's a couple types of VPNs, remote access or intranet/extranet, where you're going site to site. The VPN system can be classified by tunneling protocol used to tunnel the traffic, the tunnel's termination point, type of topology that the connections are using, if it's site to site or network to network, the different levels of security provided. Some operate at different levels of the OSI layer, such as layer 2 or layer 3, the data link or the network, and then the number of simultaneous connections that the VPN allows. Internally, VPN can use a number of different protocols itself. So it can use IPsec or TLS. It can also use DTLS, Microsoft's point-to-point encryption, SSTP, which is Microsoft's secure tunneling protocol, SSH, or WireGuard. And then the last one here we'll look at is Kerberos. This is an authentication protocol using tickets. It has a couple different RFCs that define it, 1510 and 4120. It was originally developed by MIT for their project Athena. In using Kerberos, you use a key distribution center, or KDC, which issues a ticket granting ticket, or TGT. The client, or clients rather, use this ticket granting ticket to request or receive a ticket from that server, the TGS, and they'll request those per service or service principal name. So there's different protocols out there. We're really going to kind of dive in and focus on SSL and TLS as part of this training. So to start out, we're going to look at the protocol itself, some of the history around the protocol, and the details of what happens when a client actually starts a connection and proceeds through that handshake with its server. Let's see, the controls weren't working. Oh, I was at the bottom. Okay, so SSL, there's an image of the RFC that defines TLS 1.2, and we'll start out with the history and kind of goals of TLS that provide to you as a user. So there's three main goals: authentication, confidentiality, and integrity. The server is typically authenticated by default in a TLS connection, whereas the client authentication is typically disabled by default or optional. If you enable both of those authentications, client and server, that's called mutual authentication. If you think of your web browser, you're only really authenticating the server certificate there. It's pretty rare for you to load a client certificate into your web browser and have the server authenticate that, but that does happen time to time. The authentication is done using asymmetric cryptography, RSA or ECDSA, or ED 25519, or it's using a pre-shared key. If you remember the acronym PSK there. The second goal, confidentiality. This is just making sure the data is only visible to the endpoints. So we don't want a man in the middle to be able to see our data going back and forth between the client and server. And integrity, this means that we're making sure the data hasn't been modified in transit by an attacker. So we're really trying to prevent against a man in the middle attack with TLS. This shows you kind of the sub protocols of the SSL TLS protocol prior to TLS 1.3. You can see this is kind of a simplified diagram of the OSI model, where TLS is sitting on top of the transport layer, kind of in between the transport and application layers. The blue boxes here are sub protocols of SSL: the handshake protocol, change cypherspec, alert, and record layer. The green boxes here are examples of application protocols that can sit on top of SSL and TLS, or if they're just sitting on top of regular TCP/IP or the transport, they would just be the unsecure version. For example, HTTP versus HTTPS. And here we have TCP/IP underneath, but it can be different transports as well. When a client first connects to a server, it goes through what's called the TLS handshake process. This is kind of a simplified diagram of that process, where you have a couple of round trips. The goals are to exchange certificates, authenticate the peer, set up the shared keying material, and then you end up with a secure connection once you've reached the bottom. TLS uses what's called a cipher suite to essentially represent the algorithms and modes used to secure that connection. So this is a TLS 1.2 and prior cipher suite format. It starts out with the protocol, the key exchange algorithm, a bulk encryption algorithm in an optional mode, followed lastly by a message authentication function. And if you've ever worked with TLS or configured a web server with TLS enabled, you've probably seen cipher suite strings. Here's some examples of the TLS 1.2 cipher suite strings. SSL itself was invented in 1995. Tahar El-Gamel is kind of known as the father of SSL. Netscape was the company originally working on SSL. Partway in its history, it changed enough that it warranted a name change to TLS, or Transport Layer Security. So that's the modern versions of the protocol are now TLS. And then there's been a parallel kind of spec in development to TLS and SSL, which has been called DTLS. That's datagram TLS. And that's a version of TLS designed to be run over unreliable protocols, such as UDP. This gives you the historical timeline of the protocol, starting in 1995 with SSL 2.0. There were two versions of SSL proper, 2.0 and 3.0, which were made public. Both of those are now insecure. And you'll see those if they're in a library, disabled by default at this point or completely removed. In 1999, the protocol had changed enough that it switched to TLS or transport layer security. TLS itself has gone through 4 revisions, 1.0, 1.1, 1.2, and 1.3. TLS 1.3 is the most recent that was just finalized in 2018. And then, as I mentioned, DTLS has been paralleling the TLS development with now 3 versions out, 1.0, 1.2, and 1.3. Each of these protocols is defined in an RFC. So if you want to get all the specific details of the protocol and see how it works at the fine granular level, you can look up the RFC that you're curious about here. TLS 1.3 being the most current was RFC 8446. The one in the diagram here is TLS 1.2. TLS 1.3 was, pretty exciting to track the progress of that. It spanned 5 years and went through 28 drafts before it was finally awarded the final RFC version. And when we look at TLS 1.3, we actually have a separate slide deck, which will go into more details on it in specifics, but in general, it's faster in performance for you as a user. So TLS 1.2 and before took 2 complete round trips to complete the handshake, and TLS 1.3 only requires 1 complete round trip. So if you're on a high latent network, this means the network latency has less of an impact on your handshake establishment times. And optionally, there's a new mode called 0 RTT or 0 round trip time, where you can send data in the first flight, kind of along with the first client hello. And so if you're using a protocol that benefits from having data upfront earlier, that can be beneficial. This chart's just showing that the lower impact on the network latency has on TLS 1.3 versus 1.2. TLS 1.3 is in green here and 1.2 is in blue. Latency is increasing on the y-axis, and the full handshake time is shown on the y-axis. So as latency increases, it's the connection time is a bit better tolerating the latency than TLS 1.2. And that's predominantly due to the fewer round trips. The other big advantage to you is that it's more secure. So the protocol designers took out a lot of the old legacy insecure features and algorithms. Some of those were RSA key transport, RC4, the stream cipher, CBC mode ciphers. There's been a couple attacks on those. The SHA-1 hash function now has been deprecated in favor of SHA-2, arbitrary Diffie-Hellman groups, and also export ciphers. So we linked this once yesterday. We've got kind of a good landing page for TLS 1.3, which is a good starting point. But we'll also be covering more details on this in a later presentation today. I mentioned TLS typically runs on top of TCP/IP. That's the most common use case, but it doesn't have to. Since it's just sitting on top of the transport layer, that transport layer can be anything that you have available. We've had customers run wolfSSL on top of a serial connection, proprietary transport layers, or even just over a memory buffer where there's no network involved at all. So if we look inside of the TLS protocol, there's 4 sub-protocols. There's a handshake protocol, a change cipher spec, an alert, and a record protocol. The handshake protocol is what's done up front. It's responsible for negotiating the session. That includes the session identifier or ID, the peer certificate, the compression methods being used, the change cipher spec, master secret, and if that handshake is resumable. The second sub-protocol is the change cipher spec protocol. This essentially just signals transitions in ciphering strategies. It's sent by both the client and server, and we'll see how that works here in a second. And it notifies the receiving party that all the records after this will now be protected under the newly negotiated algorithms and keys. The alert protocol does what its name indicates. It conveys alerts along with a severity and description of that alert. They can be either warning or fatal alerts, where a fatal alert will end up in the immediate termination of that connection. And the alerts are encrypted and compressed by the algorithms and keys negotiated in the connection. Then the last one is the record protocol. So this is a layered protocol that's responsible for fragmenting and encrypting and sending data. So on the sending side, you're going to see the sending party fragment the input data into blocks. This input data would be whatever your application is handing to it. Optionally, it compresses that data. That isn't used very commonly. It applies a MAC, encrypts that, and then it transmits the result to the peer. So here's a visual representation of that happening. Your input data coming in being fragmented up to the maximum fragment size up to the 14 bytes. Compressed, if that's enabled, a MAC applied, encrypted, that data is encrypted, and then TLS record headers applied to that series of bytes. On the receiving side, it undoes that, so it strips the record header off, decrypts the data, verifies the MAC, decompresses if needed, reassembles the data, and then hands it back to your application or the higher level protocol. There's a TLS record header that's applied to the message. This is a 5-byte header, and so the first byte is the record type. That indicates one of those four, well, one of the three protocols, in addition to application data. So either change cipher, alert, handshake, or application data. This next 2 bytes are the version, so that'll represent the protocol version. And then the next 2 bytes are the length of the data coming next. Now let's look at what happens during that handshake process. We'll just step through the messages and see what's in those and what they look like when you look at them in Wireshark. So the client hello is the first message that goes across the wire. It includes the protocol version, the client random value, the session ID, which is either 0 or set if it's resuming a session using IDs, the cipher suites that the client supports, compression method, if that's being used, and then any number of extensions that can be applied to the client hello. If you look at that in Wireshark, this is what it might look like. You've got some of those things in here. You can see the version is TLS 1.2. The session ID is 0, so we're not resuming a session. We can see there's 24 cipher suites being offered by the client here. And then we've got some extensions attached on at the bottom for elliptic curves, signature algorithms, and extended master secret. The hello verify request, this is sent in response to the client hello by the server. And it can just include a stateless cookie, which can help prevent against a DDoS attack. If this is sent back by the server, the client should send another client hello, again with the same cookie in it. The server hello is up next. This is sent in response to the client hello when the server can find an acceptable set of algorithms and it agrees on some of the other things in the client hello. So it includes the protocol version that it's chosen to use, the random value, the session ID that it's assigning to this connection, the cipher suite that the server wants to use and has chosen, the compression method that has been chosen, if any, and then also some extensions can come back as well. This is what that might look like in Wireshark. So here you can see it's TLS 1.2, the session ID that the server's assigned to this session, the cipher suite that it's picked, ECDHE RSA with AES 256 GCM, SHA-384. And then it's just echoed the extended master secret here, indicating that we'll be using that. There's some hello extensions, as we saw a couple of those on the Wireshark traces. A few of the common ones are signature algorithms, which indicates what signature and hash pairs could be used. There's also a maximum fragment length extension, which can essentially negotiate down the maximum size of a TLS record fragment size. There's more of those extensions, and if we get time towards the end of our day today, we'll look into that. The certificate message comes back from the server. So this includes the server certificate chain. Commonly, does not include the root CA cert, but just the peers or servers certificate, as well as any intermediate CAs that might be needed. These are X509 v3 certificates, just like the ones we looked at yesterday during our X509 session. And it must be compatible with the selected key exchange algorithm. So meaning, RSA or ECC. This is not sent when using PSK or pre-shared key cipher suites, since we won't be using public key algorithms during those connections. And when the client receives this message, it validates the certificate chain on its side and goes through the client the authentication of the server. This is what the server certificate might look like in Wireshark. You can see this one has a length of 2,393 bytes. And you can expand out the certificates section there, and you'll be able to see all the details that you would expect in the certificate. The server key exchange message, this is sent when the certificate message doesn't have enough data for the client to exchange the pre-master secret yet. So for ephemeral DHE or ECDHE suites, this contains the server's half of the key agreement, and it's signed by the server's private key. If we're using pre-shared keys, this just contains the server's key name. Here's what the server key exchange would look like. This is in the case of ECDH being used. You can see that we haven't expanded it, but the ECDH server parameters would be listed. There's a certificate request message. This can be sent by the server if we want to do mutual authentication, or if the server wants to authenticate the client. It's essentially requesting that the client then send its certificate back to the server. This is what that looks like in Wireshark. And then the kind of last message of that flight from the server is the server hello done message. This indicates the end of the server hello, and then after the server sends this, it's going to wait for data from the client. That's a pretty simple message in Wireshark, as you can see here. So the client, if the certificate request message has been sent by the server, the client will send back its certificate. This can be an empty certificate chain if mutual authentication isn't being done. If it is not empty, it's also going to contain X509 version 3 certificates, and kind of the same details that we saw in the server certificate message going in the first direction. It looks very similar to to the server certificate in Wireshark. The client key exchange message for RSA cipher suites, this contains the pre-master secret, which has been encrypted with the server's public key. For ephemeral DHE or ECDHE cipher suites, this contains the client half of the key agreement. And then after the server receives this message, now both sides of the connection have enough information that they can go ahead and generate the master secret and derive the session keys, which is done using a pseudo-random function. There's what our client key exchange looks like in Wireshark. You can see here we're also using ECDH, and although not expanded out, has the ECDH client parameters. The certificate verify message sent from the client sends this, which is essentially a hash of the handshake messages up to this point, and it's only sent if the client has sent the certificate message. It's signed with the client's private key, which allows the server to verify that the certificate matches the private key that the client is holding. This is what the certificate verify message looks like in Wireshark. The change cipherspec message is sent both by the client and the server. It's not part of the handshake protocol. If you remember, this is a separate sub-protocol than handshake, but it still happens as part of the handshake process. It indicates to either side of the connection that now the connection is going to switch over and use the newly negotiated cipher suite and keys. It's a very simple message in Wireshark. And then the finished message is the last message of the handshake. It's also the first message encrypted using the newly established keys. It contains a hash of all the handshake messages up to this point, and it verifies that the authentication and key generation was successful. So we went over the TLS record layer. There's also a TLS handshake header that gets applied. There's the first byte of that is the type, which you can see listed on the upper right of the slide here. That's essentially what type of handshake message from our previous walkthrough. And then there's 3 bytes that indicate the length of the upcoming data. And as you're looking at the wire after this, you might have multiple messages coming one after the other. So when we process a data stream from wolfSSL, we'll read off the first 5 bytes of the TLS record header, look at the length, and then allocate memory to read in the next message fragment there. So I mentioned that each side of the connection calculates a master secret, which is then used to derive the session keys. So this is 48 bytes long, and it's calculated using a pseudo-random function, which takes in the pre-master secret, the string master secret, and then a client concatenation of a client hello and server hello random values. And those are sent over in the client and server hello messages. So just kind of one excerpt here, different than the protocol itself, but interesting to see. I don't know if you've looked at this website from SSL Labs called SSL Pulse, but it gives you kind of a insight into the landscape of the top most 150,000 enabled TLS websites based on Alexa. And so it's always been interesting to look at and see how that changes over time. We can pull this up real quick. So it'll give you, essentially 60% of the top 150,000 websites, they consider secure. They get a distribution of grade between A and F. And then you can dive into, what protocols do those websites support, what key exchange algorithms. And so these are some of the things that we saw being negotiated in the handshake process. And it goes on and on, as far as algorithm support and vulnerabilities that things are exposed to. So just kind of an interesting link. They also have a server test, which can be helpful. You can plug in a server URL or host name, and it'll test that and give your server a grade from an A to an F. So it's always kind of fun to plug in some of your favorite websites or services that you use and see what kind of grade they get for TLS. And then SSL Labs also has a browser test. So if you want to test the browser you're using and see how the TLS integration of that is rated, that can be kind of interesting too. So in summary, over this session, we covered the history of TLS, the versions, and how those versions came about as far as timeline went, the sub-protocols of TLS and the record formats, and then just a little bit about widespread use with the SSL Pulse. All right, so now we're going to move on to our next section. The next section we'll be talking about is some basic usage of wolfSSL as a library. So the first thing, if you're an application developer looking to use wolfSSL, the first thing you should be concerned with is that your application is compiled with the same preprocessor defines that the wolfSSL library has been compiled with. If these are mismatched, you can run into some really weird runtime problems or seg faults. Things like our math library, if it was compiled with certain settings, but those defines aren't set when you compile your application and your application tries to use our library, things can go wrong as far as mismatches. Now, if you're using autoconf and configure, our configure script generates a header called options.h, formerly, wolfSSL/options.h. And what it does is dump all of the preprocessor defines that were used to compile wolfSSL into this header. So it makes it super easy from your application perspective that you just include this one header as your first wolfSSL header, and you're good to go. If you're not using AutoConf, then that user settings.h header could be a good way as well to make sure you're consistent with settings across library and application. After options.h, the first SSL header you'll want to use is wolfSSL/SSL.h. This is where most of our SSL API is going to be located, as well as some of our OpenSSL compatibility API. wolfSSL has two main structures for you to use. A wolfSSL CTX is a context. This is a structure that's mostly used as a factory for sessions. And then the wolfSSL structure is a session, represents a session. An application would typically have one context, and then it could have multiple wolfSSL structures, per session if you have multiple connections. You can initialize the library by calling wolfSSL init. For debugging, if you've compiled in debug support to the library, that's done with either enable debug with configure or by defining debug_wolfSSL. You can, at runtime, enable debug logging by calling wolfSSL_debugging_on. And then if you need to, at runtime, turn that off. You can call wolfSSL debugging off. Debugging by default will be output to standard error using fprintf. But we have a way you can override a custom logging callback to push that towards wherever you want logs to be going. You then create a new wolfSSL context with wolfSSL CTX new. This function takes an argument of a version. So here we're creating a TLS 1.2 client context. And we have version APIs for all the protocol versions and client and server. So there's also a TLS v1 server method, for example. Next, you could set or control how peer verification is done using the wolfSSL CTX set verify function. This takes in a pointer to your context, an argument that indicates how you want verification done. So SSL verify peer will enable peer verification. And then the last argument there is a callback that you can write. So here we're calling a function we've written called myVerify. And when verification fails, wolfSSL will call that callback and give you some extra details. It allows you to inspect the certificates, look at what went on there, and then optionally you can override the verification at that point if you want to skip certain checks or continue the connection anyway. Peer verification is turned on by default for servers on the client side, and it's turned off by default for clients on the server side. Next, you want to load in your trusted root certificates to authenticate your peer. The first function here loads those in from a dir formatted buffer, wolfSSL CTX load verify buffer. So you can see it takes a pointer to the context, a buffer, the size of the buffer, and then the format, which is either SSL file type ASN1 is dir, or we have an SSL file type PIM if you're using a PIM formatted buffer instead. If you'd like to use a file, you can load a PIM formatted file using wolfSSL CTX load verify locations. That takes the pointer to your context, a path to your certificate. After that, you're going to go off, your application is going to create a socket, connect the socket, and then you'll go and create a new wolfSSL session for that connection using wolfSSL new. This creates the wolfSSL structure and returns a pointer to a wolfSSL structure. If you're using TCP/IP with sockets, you'll pass the socket descriptor to wolfSSL using wolfSSL setFD. At that point, wolfSSL will essentially use that socket descriptor for operations for sending and receiving data internally. You're ready to do the handshake now, so you can call wolfSSL connect on the client side or wolfSSL accept on the server side. When this function finishes, it'll do that whole handshake process that we walked through in the previous deck. And when it finishes, you're down at the bottom of that process where you're just ready to send and receive data securely over that connection. If it's successful, it returns SSL success. Otherwise, it'll return SSL failure. And we have a separate API that you can use to call to get an error code. At this point, you're ready to write data or read data. You can write data using wolfSSL write. That just takes a buffer and a buffer size. You can read data. Again, giving it a buffer to read data into and the size of that buffer. And then when you're all finished, you can shut down the TLS session with wolfSSL shutdown. This handles the TLS shutdown routine where it sends a close notify alert to the peer. And then optionally, you can wait, you can call wolfSSL shutdown again to wait for and receive the peer's close notify alert. When that's just another note on that, when you do shutdown in both ways, where you send your close notify and you wait for the close notify to come back, that's called bidirectional shutdown. And you'd usually want to do that if you're going to keep using that socket after that, session has been shut down. Finally, when you're done, doing TLS operations, you can free up your resources. You can free the SSL session using wolfSSL free the context with wolfSSL CTX free, and then free the library resources by calling wolfSSL cleanup. For API details, we've got our wolfSSL manual, and inside of that, we have wolfSSL API reference. Kind of a nice thing just to note, in the last year, we redid our wolfSSL manual. So now it's generated every night based on our current state of our documentation in our GitHub repository. So now you'll be able to use the latest and greatest documentation from night to night. Also, for a usage example of API, you can look at our example client. That's under examples/client/client.c. That is getting a little bit big now, as far as, it has a lot of features that it can do. So we also have some smaller examples available in our wolfSSL-examples repository, which is up on GitHub as a separate repository from wolfSSL. As we saw yesterday, you can use the wolfcrypt API individually. We saw that there's typically one header and one structure associated with an algorithm. A lot of customers just need to use a subset of cryptography. Maybe they're just, generating a hash or signing a hash. So they need SHA-256 and RSA or something like that. And you can compile out all the TLS code. We have a build option that allows you to only build the wolfcrypt library. For wolfcrypt API details, we have a wolfcrypt API reference. That's also in the wolfSSL manual, same place that you'll be finding the wolfSSL API reference. They're just in Appendix A and Appendix B. I think we did note this at one point yesterday. As we've designed wolfSSL, we've tried to keep portability in mind. So we have a lot of abstractions, and we'll be looking in, I think this afternoon, into how you can customize wolfSSL and some more details that you'd want to be concerned with when porting to your platform. We also mentioned user settings as just another reminder of, we recommend using a custom user settings.h header file, where if you build wolfSSL with wolfSSL_user_settings, wolfSSL will automatically include a user settings.h header. And you can put all your customization defines for wolfSSL into that file. And we've got some examples under either the ID rally cross ARM directory, or there's an example /configs directory with a few in there. So that gives you kind of an overview of the most basic APIs you would need to establish a TLS connection with wolfSSL. You can see that really there's not that many APIs needed in the most basic case. But going out from that, there's a lot of edge cases and different use cases that people like to do. And so we do have a lot of different supporting APIs. All right, so I just wanted to take a quick look at our example applications. Let me switch over to my terminal window here. All right, so I'm just inside of our wolfSSL repository here. Again, this is what you'd see if you just cloned wolfSSL right from GitHub. If you remember, the first thing we did was run autogen.sh. Since if you download wolfSSL from GitHub, you need to run autogen.sh as a first step. That'll generate your configure script. We already did that yesterday, so I'm going to skip that here for time. We're going to run configure. We won't give it any special options here since we're just looking at our generic example client and server. We'll wait for that to finish configuring. Go ahead and build the library with make. This builds the library, and if you remember, also builds the examples, the wolf grip test, the wolf grip benchmark, and our unit tests. Now, under the examples directory, we have a few different things. We have an example client, an example server, example echo client and echo server, and a few other items as well. If we look under examples client, we'll see that we have a client.c file. We've also got some supporting files in there for Visual Studio solutions and projects. When we run make, we can see that the examples get compiled. We have a client here, but remember when we're building a shared library, that client is actually just a wrapper for AutoConf, and the real client is under examples client.libs if needed. But for our sake, when you're running it, you would just run example server or example client. And that script handles setting up all the right paths that it needs to use to find the library and execute the executable under the .libs directory. If we look under example server, you'll see a very similar thing. There's a server.c, server.h. Each of these, so if we do example server, each of the client and server, you can do a -- help and see the help menu come out. We have a good amount of options here now, everything from specifying the version of SSL or TLS. You can tell it what cipher suites you want to use. So this is a delimited list. Pass in the certificate file that you want the client or server to use, the key file, which is your private key, the certificate authority you're going to be using to authenticate the peer with. A couple other ones. If you need to disable peer authentication, you can use -d. If you want to bind to any interface on the server side, you can use -b. Otherwise, we'll just use localhost. If you have pre-shared keys or DTLS enabled, you can use -s to use pre-shared keys, or -u to use DTLS instead of TLS. We have an option that it's an API and exposed as an option in the client and server that allows you to group packets together. So if you want to send fewer packets over the wire, some options for session resumption and a number of different other things. On the server will shut down after one connection by default. If you want it to stay open and accept multiple connections, you can use -i. If you want to return a basic HTML web page from the server, you can use -g. Seeing what other common ones here people like to use. Yeah, so there's some other kind of use case scenarios that we have options for in the example server. If we look at the example client, you're going to see something very similar. Same options for setting version, cipher suite, certificate key, CA certs. One helpful one is there's a -e, which will dump out all the enabled and available cipher suites that the client has available to it. Sometimes you're not quite sure, what the cipher suite string should be that you pass in to set. So if we did example client -e, you'd get a list of delimited cipher suites. Sometimes you can, if you're interested in only a certain algorithm, you can grep based on that to help you narrow down onto the cipher suite strings you're interested in. If you want to send an HTTP GET message, you can use a -g. By default, the client just sends a string. I think it's hello server, and the client and the server will send back a response string. Again, if you want to use DTLS, use -u. That would have to be also compiled into the library. We talked about bidirectional shutdown. If you want the client to wait to receive the server's close notify alert, you can use -w. If you want to disable peer authentication, you can use -d. All right, so let's try a simple connection here. I'm actually going to switch this to show you my screen just so you can see two windows at once. All right. Here we've got one window. We'll open up another window. Make the text a little bigger so you can read it a little easier. So on the left side, we're going to start our example server. That's just listening now on localhost port 11111. And then if we start up the example client, we can see that the client connected to the server using TLS 1.2 with ECDHERSA, AES256 TCM SHA-384. It gives you the curve name that was used, SECP 256R1. The client sent hello wolfSSL, and the server sent back I hear you shizzle. Let's see, what else could we do with the client? You could connect out to an external website. So if you want to connect out to wolfSSL.com on port 443, by default, you'll get a signer error since we don't have the right root CA loaded. If we want to disable verification, we can use -d, and it'll go ahead and make that connection. We'll come back. One of our next exercises is to find the correct root CA, so we'll look at that in a bit here. It's stalled here just because the web server doesn't know how to understand hello wolfSSL, the string. So if we want to send an HTTP GET message, we can use -g. It just sends kind of a canned response, which of course the web server doesn't know, have the right page to respond to in this case, but at least it sends us back a response. Let's see. See, I think that's probably good for now. We're going to come back to these guys here in a minute too. But let's go ahead and move on to a few notes about finding the correct root CA. So this is one of the more common support questions we get that comes up internally for our support team, is that you're using, our customer or user is using the incorrect root CA and verification is failing when they're trying to connect against a server. So wolfSSL requires the topmost certificate or the root certificate or the root CA to be loaded as a trusted certificate in order to verify the chain. So here we have an example chain A, B, C. If that gets sent from the server to the client, if B and C, C being the pure cert, B being an intermediate cert, are sent by the server, wolfSSL needs to have A loaded as a trusted certificate to verify the chain. If only C is sent, so that's only the server certificate, then wolfSSL would need to have both A and B loaded as trusted certificates in order to walk up the chain and get from C to A and verify the correct chain. So the root CA, we saw this diagram in our previous slide deck on X509. This is just a Google certificate chain example. The root CA is that top certificate, the Equifax Secure Certificate Authority. And it has two intermediate CAs, the GeoTrust Global CA and the Google Internet Authority G2. And then the last server certificate is the one for Google's web server, star.google.com. So if Google just sends, if they send their root or their peer certificate at the bottom plus the two intermediate CAs, wolfSSL would just need that top green certificate loaded as a trusted root. On the other hand, if they just send their server certificate, star.google.com, then you would have to load the top three certificates all into wolfSSL as trusted CAs. There's a couple different ways you can find the right root CA for a server. So one way you can use is your web browser. You can click on the lock and look at the certificate details, and there's usually a way to export the certificate out of there. Second way you can use, which is the OpenSSL's S-Client application. It tells you the certificate chain details when it makes the connection. And typically the root is not sent as part of the chain, but you'll be able to see the common name of the root certificate. And then you would take that, do a Google search, and that would typically take you to the CA where you could download that root certificate from. Now, sometimes when you do those two steps, they're going to vary and you're going to see different root CAs. And sometimes that's a little confusing. And sometimes why this happens is, the command line OpenSSL application can sometimes hit a load balancer and it doesn't know or get redirected to the end server. Whereas your web browser gets, it follows the load balancer's request and gets redirected to a different end server. And sometimes those have different certificate chains loaded on them. So we're going to go through a little demo of finding the correct root certificate. Okay, so we're going to start in our browser here. We're going to go to wolfSSL.com and try to find the root CA for our own website here. So we can click in the browser. We can click on connection is secure, certificate is valid, details. Here we can see the certificate chain information. So here it's saying that wolfSSL.com has a global sign certificate chain ending up in an issuer global sign root CA-R3. So let's try to export this certificate. I'm going to put it on my desktop right in the training directory. Now if we go, I'm going to switch over to my desktop again so you can see this. We back up, we're inside of, I have this training directory on my desktop. You can see there's a global sign.cer in there. If we're not really sure what format this is in, why don't we just open it up and look? And oh, here we can see it's in PEM format. So it has a begin certificate and end certificate, header and footer. It looks like it's base 64 encoded. And that's the first way. So now let's look at the second way. By using OpenSSL S client, we can do connect wolfSSL.com 443, and it'll dump out a bunch of details about that connection. But if we scroll up a little bit, here's our certificate chain details. So we see that here we're hitting our Fastly cache server. Issuer is global sign Atlas R3, etc. That certificate is issued by the global sign root CA-R3. Now, interesting note, if you want to see how this can differ sometimes, if we take off www, I think we're going to get a different chain. Yeah, so here we're getting a different chain now, where our root certificate authority would be a GoDaddy root certificate authority -G2. But now we're going to first we're going to see if we can make a connection with our example client using this global sign certificate that we downloaded. So let's go over here onto our right window. We do examples /client/client-h www.wolfSSL.com. -p is the port 443. -a specifies our CA certificate. Here we're going to go up a directory to global sign.cer. Then since we're connecting to a web server, we may as well send our HTTP GET request using -g. So there you can see that worked successfully. We connected using TLS 1.2, using the Cyber Suite, which is using ECDHE, with that ECC curve being on the SECP 256R1 curve. Again, it didn't find the exact HTTP page that we were requesting, probably since they don't have it available there. But the connection did succeed. Now let's see what would happen if we have a wrong certificate. So let's go back and find this other CA. If we look, we're looking for the GoDaddy root certificate authority -G2. I'm going to copy that, go over to Google, search for that. GoDaddy has a CA cert repository page. And it looks like this first one is the one we're looking for, GoDaddy Class 2 Certificate Authority Root Certificate G2. So we'll click on that. That gives us an option to download it. We'll put it in the same directory. Let's go back here. Now we have a new gd root-g2.crt. If we look at that one, we see that's also PIM encoded. Now let's try to connect. If we try to connect to the same www.wolfSSL.com on port 443 using this new GD route, we should get an error. Yeah, so here comes back. This is what you're going to see if you have the wrong root CA loaded. There's a negative 188 ASN no signer error to confirm failure. So that means you have the wrong root CA or root CAs loaded to successfully verify your server chain. Since when we did the OpenSSL S client, we were actually using wolfSSL.com, which goes to a slightly different place. Let's hope that this one actually does verify that location. And there we got a successful connection back. So that's one of the most common problems. Hopefully that helps you get past that, or at least start looking in the right direction. Another helpful thing, we're going to look at Wireshark in a little bit, but that's another way you can use to inspect certificates, is that you'll see them in the Wireshark trace of a connection if you don't have one of these methods available, or you're just connecting to an embedded device that's harder to extract data out of. Get into is debugging wolfSSL. So just a couple notes, a couple of facilities we have available to you to help you get past your problems that you run into. Some of those aren't obvious out of the box without enabling some more logging or looking into the connection in a little more detail. So yeah, like I was talking about, using effective debugging strategies can really help speed up your development time and troubleshooting. It also will help you more effectively communicate back to our support team and get you familiar with some of the information that our support team would be looking for to help you get past your problem. And we have some built-in features to wolfSSL, which will help you with debugging your errors and problems. We have a debug build, which spits out a log, an error log. And that logging mechanism is flexible in the sense that you can write and register your own logging callback and push those logs to the locations that you choose. We've got error codes internal to wolfSSL, as well as some descriptions of those error codes. And we find, using our example client server can also help your debugging. So first of all, let's look at our debug build option and what that does. We mentioned it briefly a couple slides back, but we do have an enable debug configure option. When this is enabled, it'll enable debug symbols in wolfSSL, as well as if you enable debugging at runtime, it'll output a debug log to standard error by default. If you're not using configure, you can define debug_wolfSSL, and then at runtime, you can enable or disable that log by calling wolfSSL debugging on or debugging off. So what does the log show you when you do enable debug logging? It shows you a bunch of things. It shows you when wolfSSL is entering and leaving functions. It shows you details of the handshake process. It really gives you more context around the error that's happening. You also see some details there about certificate parsing, and if you run into an error when wolfSSL is trying to parse a certificate, you might see some additional error messages coming out in the log. We have some kind of more granular debugging if you need to go further than just our generic debug log. Usually you don't need to get to this step, but if you want to print out the actual keying material that wolfSSL is using, we have a define called wolfSSL_debug_TLS. And this will print out the bytes of data that are being sent and received, the extension data, and then the key, public key information, whether that be Diffie-Hellman or ECC RSA or Curve 25519, etc. We also have a show secrets defined, which again isn't usually used, but if you do define this, it'll print out the client and server random values and also the pre-master secret. Now, these last two defines that enable more output of keys and secrets. Obviously, you don't want to enable that in your production environment, only when you're debugging and working through a problem. One more define that we have is called wolfSSL SSL keylog file. And when enabled, this will cause wolfSSL to actually open and write to and close a file called SSL keylog.log. And this outputs some pre-master secret logging information that you can load into Wireshark to help Wireshark decrypt a connection. If you do define this, you also have to use the show secrets define as well. Now, when you do run into a problem, you're going to see an error code show up. And most wolfSSL and wolfcrypt error codes are negative values. Some examples of common ones that you'd see is -173. This is a bad function argument. -188. We saw that in our at the end of our last session, where you run into when you don't have the right CA or root certificate loaded to verify the peer. Some of our APIs return wolfSSL success or wolfSSL failure instead of an error code directly. In this case, after you receive a wolfSSL failure return from those APIs, you can then go on and call wolfSSL_get_error, passing in a pointer to the wolfSSL session structure, and that'll return the underlying error code to you. To look for our error codes, we store them in two separate files, depending on if you're at the crypto level or the SSL level. The wolfcrypt error codes are in wolfSSL/wolfcrypt/error-crypt.h. wolfSSL error codes are in wolfSSL/error-ssl.h. We also have associated string descriptions with an error code, since sometimes the error code itself is not very descriptive. These are available to you unless you explicitly compile out the strings. Sometimes people want to do that to reduce footprint size of the library. If you do want to compile out error strings, you would define no_error_strings. The error string size defaults to a maximum of 80 bytes or 80 characters. You can define this if you need to override it for some reason, but most people aren't going to need to do that. We have a function called wolfSSL error_string, which takes in an error number and then returns the associated string with that. And so that's one that you'd want to use at your application level if you got an error code and maybe you weren't able to actually go look in the source code of wolfSSL to find the string, or you just wanted your application to print out the respective string for that error code. So some examples here: -323. The error string for that is non-blocking socket wants data to be read. -326 would print out record layer version error. So a few tips and tricks. We recommend, or one thing I found helpful is using our example client or server to help you debug. So most of the time you're only going to be writing or working on a server or a client at one time, and testing against our example client or server gives you a known working endpoint to put on the other side of that connection. So if you're developing a client, you can try to connect your client to our server. If you're developing a server, you can use our client to try to connect to the server. And it gives you some confidence that the other side of the connection is working. It also allows you to enable some debugging and see what's happening on the other side of the connection if needed. Wireshark can be a very helpful tool. We use this all the time internally when working with customers and users. It's able to capture TLS traffic essentially, and allows you to drill into each message down into the details. It's also helpful. You can export a PCAP file from Wireshark and send it. You're able to send that to our support team so that we can better see your connection and help you diagnose a problem. It does capture all network packets on a specified interface. It decodes them in real time, recognizing that they're SSL or TLS or DTLS traffic. It allows you to do filtering based on ports or IPs or really off any of the details that you can see in Wireshark. And in some conditions, you can actually decrypt traffic if you need to see application data. So yeah, decoding traffic. You can't easily decode DHE or ECDS DHE traffic since those are using ephemeral keys. If you're using a static RSA cipher suite or a static ECC cipher suite, you can just load that static RSA key into Wireshark and it'll decrypt traffic on the fly. So what are some common issues that we see from our users of wolfSSL? These are a couple of them that come up. So wolfSSL read or wolfSSL write fails with a -323 error. And so 323 is essentially a non-blocking error. And it just means that the underlying IO would have blocked and that the application should then loop around and retry to call the API again with the same arguments that you called those APIs with the first time. So that one's an error, but not really an error, just an indication more so to your application. The next one is a bad version error, -326. So this could be, one cause of this could be that you try to connect your client and server using different versions, different TLS, SSL versions, and it can't negotiate because of those mismatched versions. Another common one we see is a -501. This is a cannot match cipher suite. So here your server doesn't have any common cipher suites that the client's requesting. So here you'd either need to enable more cipher suites in your server or adjust the cipher suites that your client is requesting. Sometimes this is also caused by using the wrong type of certificate and key. So if your server only supports ECC cipher suites and you try to connect using an RSA key, private key and certificate, that can also be a problem. So in that case, you just need to, make sure that your server supports what your client is trying to use. Another error we sometimes see, -155, bad signature on certificate. This one is sometimes caused if you have if you're using a mismatched private key and certificate. So yeah, say you start up, your client or your server, and the cert and the private key you use are not the right combination, so they're not the corresponding key pair. And then the last one here, -188. This is a no signer certificate error that we saw, meaning your client or server has the incorrect root CA or certificate chain loaded to verify your peer. All right, so we're going to do another look into wolfSSL. We're going to try to enable debugging and see the log that comes out. Look at some of the error code and string locations, and then try out Wireshark and show you what that looks like there. So let me switch back over to my desktop here. So I'm going to use this window here in the middle. I'm going to do a make clean, which cleans up all the object files and library artifacts, so we can reconfigure with enable-debug. If you weren't using configure, remember you could define debug_wolfSSL to achieve the same effect. So we'll wait for configure to finish. Run make to recompile the library. Okay, now actually I'm going to split this up. Go back to our wolfSSL on the left side too. So if we start the server up on the left side, now we can see a lot of debug messages starting to come out. We can see entering and leaving functions. So here you can see our server's calling wolfSSL init, creating a new context. This is that function I mentioned regarding certificate chains. So wolfSSL ctxd certificate chain file will load in a certificate chain to the server. And then this debug here is inside of that function as we decode some of the certificate information. It's loading in, the server's loading in a private key here with wolfSSL ctxd's private key file. It's enabling verification. It's not obvious from just this line in the log, but we do enable verification of the client by default in our examples. It's loading in CA certificates to use to verify the client. This is all some details about us parsing those certificates and adding it as a CA internally. It's creating a new wolfSSL structure with wolfSSL new, and then we're essentially waiting now for a client connection. So if we start the client up, in our other window, we've got debugging going on in both windows now. If we go up to about where we were, we're not going to go through all this, but I'm just going to call out some of the key areas. Okay, so here we were at wolfSSL new. You can see we passed our socket descriptor to wolfSSL with wolfSSL set FD. Here you can see this. Now we started the handshake with wolfSSL accept on the server side. We got a handshake message. We're processing a client hello. Here's some details about some extensions we received. Here we verified the suite validity with the Cypher suite we're using to make sure we're using the right kind of keys. You'll see these growing and shrinking input buffer calls. So I mentioned by default, wolfSSL will look at the record header that comes across, look at the length in that, and then grow the input or output buffer to match the length required. And so we grew it to read the client hello. Now we're shrinking it back down. Here we're growing the output buffer to send the server hello message. Here you can see accept state represents the server's state. So we send our server hello. We send our certificate status. We're making our ephemeral ECDH key right here. We send our key exchange, certificate request, and our server hello done message. Now we got the next flight from the client. So we got the client certificates. Here we're processing the client's certificates. We get down to here and we verified the peer cert. We got another handshake message. We got the client key exchange. We're processing the client certificate verify message. We get down here. Now we're going to start exchanging change Cypher spec messages. Got the finished message, which remember that's the last message of the handshake. We're using session tickets here, so we'll go over that in a little bit. We send a session ticket. Here you can see wolfSSL accept returns 1, so we completed our handshake there. Here's our handshake details that we saw print out without debugging enabled. Then we're going on to read and write data. So here you can see, wolfSSL read and wolfSSL write debug messages. We get down here, we're freeing our memory and cleaning up the library at the end. So that's a lot of good debugging information that can come out. And if an error happens, you'll see it, pop up in the log here. One thing we could look at might be interesting. Let's just take this window to the middle to focus on it. If we do our client and we connect against an external server, wolfSSL.com port 443, and we don't provide a CA certificate, we should get an error. So if you remember, 188 is our ASN assigner error. So here we got down to, we're trying to find the CA to verify with. And you can see the log is telling us failed to verify peer certificate. There's no verify callback available. So we're just treating this as a fatal error. And we're sending an alert back to the CA. That's an alert type 48, which is an unknown CA. So if an 80 to 188 wasn't immediately obvious to you at the beginning, you can enable debug logging. You could look right here and it would essentially tell you, we failed to verify the peer cert. And that would be an indication that you have the wrong root CA loaded. All right, so let's, I guess we can look at Wireshark next. I'm just going to open up a Wireshark window. I'm not sure I can zoom in on this text. This is probably pretty small for you guys. Maybe I can actually share the window. That might be better. Okay, in the background, I'm just going to run our example client against our example server. So example server. Start that up. In the other window, I'm doing /example/client/client. And before I start that, I'm going to start listening here on my loopback interface port 11111. which is the port that our examples use by default. Okay, now we're capturing and listening for traffic on our local interface, port 11111. I'm going to start the client up. There you can see our client server just made their connection and shut down. We have our handshake traffic here. We can filter this if we type SSL in the box or TLS using the newer protocol name. It gets rid of all the other traffic except for the TLS packets. And this would allow us to go in and look at the client alone. We could drill down and see all the details we wanted about this. So the session ID is 0, meaning this is the new session. We have 24 cipher suites, which the client's sending support for. What else is interesting? Signature algorithms extension has combinations of signature algorithms and hash message digest functions that can be used for signatures that the client will accept. EC point formats is going to tell us what point formats the client will accept. And some different, there could be any number of extensions listed here. Here we have support groups, encrypted MAC, and extended master secret. We can go on and look at the server hello, the certificate message. We can dive in and see this is the server certificate. So you can see we're sending a chain back to the client here, 2 certificates. The server key exchange, since we're doing an ECDH suite, which we can see in the server hello, where it's TLS ECDHE, RSA with AES-256, GCM SHA-384. Our server key exchange message has our ECDH server parameters. Our server is requesting the client send a certificate. Server hello done. Here comes our client certificate, just has 1 certificate. You can go down as far as you want into these, if you want to look at, say, the issuer and keep going. You can also export certificates from Wireshark. If you'd right click on this certificate and export packet bytes, it would export this certificate as a DIR formatted file. So that can be helpful from time to time. The client key exchange, since we sent our certificate, we're sending the certificate verify message. The change cipher specs here indicating we're switching over to use our new set of keys. This encrypted handshake message is the finished message. So I mentioned that's the first encrypted handshake message that's sent under the newly negotiated keying material. And then we switch over. Here's our encrypted application data, which we of course can't see. If we could, it would say, hello wolfSSL, and I hear you for shizzle. And then these encrypted alerts are the finished messages coming across. Sorry, not the finished, the close notify messages. When you call wolfSSL shutdown from your application, it sends the close notify alert, which is encrypted to the peer, letting them know that that connection is shutting down. So that's Wireshark at the most basic stage. Of course, there's more you can do with filtering. There's more you can do with decrypting traffic. Of course, these are going to change. Like this is TLS 1.2, but if you use a different protocol, that's going to change. If you use different cipher suites, all these details are going to be dependent on your use case, of course. If you wanted to send this to our support team, you could go up to File. I guess we'd have to stop this first. And then in the file menu, I don't think you can see it, but there's a save or save as, and that would just export a file that you could then send on to our support team. Okay, let's see if we hit all the notes we were going to do there. Oh, error codes and strings. Yeah, we can look at that real quick. It's just, I mentioned our error codes are in wolfSSL, wolfcrypt, errorcrypt.h. And so if you go down in this file, you're going to see all of our negative error codes here. In here, our comments pretty much match the string that you would see if you retrieve the string from the application. And then if you're looking for the SSL level ones, there's a wolfSSL/error-SSL that just starts essentially at a different numbering range, but we split them out just to be succinct. and divided between crypto level and TLS level. There's quite a few error strings and error codes in the library now. All right. So let's see what we're going to go on to next here. Okay, so next up, we're going to talk about DTLS, and then PSK following that, and then TLS 1.3 after that. So DTLS, if you remember, this is datagram TLS, which is designed to be run over unreliable protocols like UDP, where you don't have the reliability guarantees that you're getting from TCP typically. So DTLS has to build up a lot of those extra reliability and retransmission things inside of the protocol itself. If you look at the spec, it's defined as changes as compared to TLS. The versioning matches the TLS version of the same version. The current DTLS version is DTLS 1.3, which just recently came out. I think wolfSSL is the only implementation available for DTLS 1.3. Again, they're defined in RFCs. Here you can see the RFCs that match various DTLS versions. The most recent DTLS 1.3 is 9147, although the snippet here on the right side is version 1.2. If you're curious about where DTLS is used, I just took this out of Wikipedia, has a DTLS page, and they have some use cases listed there. So these are public use cases of DTLS. The Cisco AnyConnect VPN client. Apparently they were the first DTLS-based VPN. Cisco Intercloud Fabric uses DTLS to form a tunnel. Zscaler 2.0 uses DTLS for tunneling. The F5 Networks Edge VPN client uses TLS and DTLS. Citrix's SystemNet Scaler uses DTLS over UDP. And then your web browser uses DTLS whenever you're using WebRTC, that uses DTLS SRTP internally. So what makes it different from TLS? There's an explicit sequence number, which has an additional epoch number with it. The handshake detects and recovers lost messages. So that's something that would typically be done by TCP. If using TLS, it allows for duplicate and replayed messages. So if things are dropped or replayed from the other side, that is handled okay by the client or server receiving those. It ignores errors post handshake, and it assumes that you're running over an unreliable transport underneath. For the handshake, each handshake has its own sequence number. The handshake can be fragmented, those messages. And the handshake temporarily turns UDP essentially into a reliable stream with retransmission. So, moving to DTLS isn't always the best choice. Some people think that the benefits of UDP being connectionless will be seen with DTLS, but DTLS kind of makes your connection, your connections into a connection-oriented client and server interaction. There's one unique handshake message to DTLS, which is called a hello verify request. We saw this in our walkthrough of the handshake, but it wasn't called out at that point as DTLS specific. And this is a denial of service countermeasure, which prevents extra resources from being used on the server side. And so it essentially includes a cookie that then the client has to include that same cookie again in its client hello, which makes it more resource intensive on clients if they're just trying to blast out a bunch of client hellos to a server. For packet loss, a simple timer is used to retransmit handshake messages. And if the peer doesn't send a message before the timer expires, we assume that packet's been lost. After the handshake, the protocol can tolerate drop packets okay. You're not losing any security through the missing packets. You might just be missing application data. So fragmentation happens for the handshake messages only. There's a fragmentation offset and a fragment size that's used internally. By default, we disable DTLS and wolfSSL just for size constraints. And most people are using TLS instead of DTLS. You can easily enable that if needed with enable-DTLS. We've got some other DTLS specific options. We have enable DTLS MTU, which allows you to override the maximum transmission unit size for DTLS. By default, that's going to be the TLS record size, which is 2 to the 14 bytes. You can enable DTLS 1.3 by doing enable DTLS 1.3. And DTLS 1.3 has a connection ID. Typically, connections are associated with the IP and host combination. But if that's not available, in some use cases, there's a new connection ID that can be used. So like TLS, you'll want to create a context with a specific DTLS version and a side being specified. So you can do that either for DTLS 1.0, 1.1, or 1.2 or 1.3. We have an API called wolfSSL_DTLS, which allows you to just kind of pull if that session has been configured to use DTLS. An API called wolfSSL DTLS get peer that returns the sock adder information that you've set for your DTLS peer into that structure or session. We have a wolfSSL DTLS set peer function, which allows you to set the DTLS peer information by passing in a sock adder in structure. wolfSSL DTLS set timeout max sets the maximum DTLS timeout. wolfSSL DTLS get current timeout gets the current timeout value for that session in seconds. wolfSSL DTLS got timeout. So if your application thinks the timeout has occurred, you can call this, and wolfSSL will try to retry the transmission, of that last message. We have our example client server that we've been looking at. Those do also support DTLS. And we also have the wolfSSL examples repository, which is on our wolfSSL GitHub organization. And in there, we have a DTLS directory, which contains examples for regular DTLS, non-blocking DTLS, resumption, multi-threaded, and also kind of a tutorial and walkthrough that goes into more details around DTLS. To use our example client server with DTLS, you'll want to use -u. That essentially tells us to use UDP DTLS. And then you should see the summary at the end. The protocol should change to DTLS at a version number that you've used. So in the wolfSSL examples repository, I mentioned we've got a couple things in there. Server-DTLS.c. This is kind of a minimal example with blocking IO underneath. And client DTLS.c is its respective client application. You can connect, those have been designed to connect against each other. Server DTLS non-blocking.c is using kind of the same DTLS logic, but using non-blocking IO. It uses timeouts and shows you how to use those inside of an application. Client DTLS shared.c. This is an example that tries to use the same wolfSSL object from multiple different threads by using a mutex protection. And so the threads don't block each other unless it's specifically trying to access that wolfSSL session. So that gives you an overview of DTLS. Let's try to connect, do a quick connection here. That's switched. Desktop, there we go. I think you should be able to see that. So if we do examples /server/server --help -u is for DTLS, enable UDP DTLS, and add -v2 for DTLS 1 or -v for DTLS 1.2. So we can do examples server -u -v2 or -v3. Excuse skipped a step. We have to actually enable DTLS at configure time. So if we do configure-help grep DTLS, we'll see we need to do --enable -DTLS. We'll wait for configure to finish here and then rebuild the library again. All right, so make is just finishing here. Then we can go back and run our example client, example server, example/server/server-u-v2. In our other window, we can do /examples client-u-v2. There we're connected with DTLS. If we do -v3, there we connected with DTLS 1.2. So pretty easy to switch over there and use DTLS with our main examples. So the third type of authentication, I guess, or second main type, apart from public key authentication in the handshake, is to use pre-shared keys or PSK, or this is just essentially an array of bytes that you treat as a key, and that key is pre-distributed to your endpoints. This is defined in RFC 4279. And so what are the differences using pre-shared keys versus using X509 with RSA or ECC? The first big one is it doesn't use certificates and public key cryptography at all. So, the public key algorithms and those operations are the most expensive performance-wise in your handshake. So if you're looking to, really optimize for it'll essentially eliminate those public key operations in performance. It might be a reason to look at pre-shared keys. It's also going to reduce your footprint size of the library considerably. The smallest buildable wolfSSL that we've done, that 21 kilobyte build, was a PSK only build. So keys are pre-distributed to endpoints, whereas X509 certificates are exchanged in the handshake. It's faster than X509 since it's skipping the public key operation. It can be a little more complex though with key management, since now you do have to manage these keys that are pre-distributed to all your endpoints, and then have a way if they get compromised to update them. These are the PSK cipher suites that wolfSSL has support for, specifically the static key cipher suites. So static key meaning that we're not using a DHE or ECDHE along with this. Then these are the ephemeral cipher suites for PSK using either ECDHE or DHE. Our static key cipher suites, not only PSK ones, but also RSA and ECC static suites are disabled by default in wolfSSL. Just for security reasons, it's better to use the ephemeral ECDHE or DHE suites that generate an ephemeral key during the handshake. If you do want to enable the static PSK suites, you can define wolfSSL_static_PSK when compiling wolfSSL. You can define all the PSK suites if you want at build time by defining no_PSK if you just want to compile them all out. Like any cipher suite, you can set a specific suite you want to use using our wolfSSL CTX set cipher list function at runtime. We have some callbacks available. So on the client side, you have to register a PSK callback to set your key. So you can register that either at the session level or the context level. If you set it at the context level, it's going to get used for all sessions. Otherwise, you can just set it at the session level individually. Our callback, WC PSK client callback, is prototyped in SSL.h with the following signature. And so it takes in the pointer to your SSL object. So these are the arguments you would get, be getting called into your callback. A hint, which is an input argument. It's an optional hint for the server to help the server pick the correct key to use. The identity argument is actually an output argument, which can help the server find the correct key. ID max length is the maximum length of the identity that you can use and store into the identity array. Key is the output array where your client should write the PSK into for wolfSSL to use. And key max len is the maximum length of that key buffer that you can write to. This callback should return the number of bytes in your key. So here's an example callback. We have this in our wolfSSL/test.h file called my PSK client callback. It's just a simple callback that you can see that we copy an identity string into the identity argument. And then we have a key that's 4 bytes long. You can see we're setting that into the key array 0, 1, 2, 3 of 26, 43, 60, 77. And we return the length of the key, which is 4. So that key that's set there should be the same as the one that's picked and set on your server side. So on the server side, you also need to register a callback by using wolfSSL set PSK server callback. You can do that at the session level or the context level, just like the client. This is the prototype for the server PSK callback. It takes an input, which isn't, well, it doesn't take an input. It gives you the identity as an argument, which is the hint that the client sent. Sometimes the server will have a table or a database of keys, and then you can use that identity to help find the right key to use. And then the key buffer is the output buffer where you need to write your PSK into. Key max length is the maximum length that key can be, essentially the size of that key buffer. And then you should return the size of your key in bytes. So here's our example server callback we have in wolfSSL/test.h. Here we're getting in the identity from the client, so we compare that to our stored key string that we have in test.h. If that's not equal, we return 0, which is an error. If that does match, we go on to set our key, which is the same as the client side was, 26, 43, 60, 77, and we return the length of that key, which is 4. Servers can set a PSK identity hint at either the context or session levels. And the server stores this identity to help the client select the correct key. You'd get that back inside of your client callback. wolfSSL supports identities and hints up to 128 octets or bytes, and supports pre-shared keys up to 64 octets or bytes. So a couple APIs you can use. wolfSSL get PSK identity will return the PSK identity back to your application. The PSK identity hint can be retrieved using get PSK identity hint. So let's see if we can use the example client and server using pre-shared keys. So we have to make clean, since we do have to recompile. If I do configure -- help and grep for PSK, we can see we have an enable -PSK option. We'll reconfigure, wait for the configure to finish here. Rebuild the library with make. Now let's look at our example server -help. So if we look here, we can use -s to use pre-shared keys. So we'll do -examples/server/server-s. And in our client, we'll do -example/client/client-s. So here we've connected using TLS version 1.2 with a pre-shared key cipher suite, DHE PSK with AES 128 GCM SHA-256. As a double check, if we want to see the supported cipher suites, we can use -E with our client. And to make that a little more clear, we can grep for PSK and see that we've got 1, 2, 3, 4, 5, 6, 7, 8. Looks like 8 or 9 cipher suites supported there that use PSK. And yeah, I think so. Again, very simple to switch over and use pre-shared keys. If we want to look at test.h, you can find those PSK callbacks that we saw in our code. So there's my PSK client callback, and my PSK server callback is right below it. So you can, those callbacks are designed to do whatever you want inside of those callbacks to find inset keys. I'm going to go ahead and get into TLS 1.3 next. We talked a little bit about it before. It's interestingly the only protocol that has its own logo, which is this logo here from the IETF, or I should say the only version of the TLS protocol that does. We talked about before kind of the advancement of TLS 1.3, that it took a while, and finally was finalized in August of 2018. If we look backwards, there's been a number of different vulnerabilities in the TLS protocol since it came out. TLS and the protocol designers were trying to make it harder for these to happen in the future by designing the protocol, with the attacks in mind that we've seen in the past. A lot of these past attacks have had clever names with acronyms that are kind of catchy. As you can see, some of these are listed here on this slide. We've seen that the RFC 8446 is what defines TLS 1.3. If you really want to, dive into the details of the protocol, that would be the document to look through. So what changed in TLS 1.3? There were algorithm changes. Most of the handshake messages are different, and more of those handshake messages are encrypted. There's a new 0 RTT mode, 0 round trip time. There's redesigned key derivation functions, removal of insecure features like we saw before lunch, and also some changes to how session resumption is done. So first of all, algorithm changes. The symmetric algorithm list has been pruned of all the legacy and secure algorithms. We saw before lunch the list of some of those that had been taken out. The remaining algorithms all use authenticated encryption with associated data, or AEAD mode. And the cipher suite concept has changed to separate the authentication and key mechanisms from the record protection algorithm. So you'll also see how some of the cipher suite notation has changed in that architectural difference. ECC is now included in the base specification. It includes the new signature algorithms, or the newer ones of ED and ED 25519 448. Point format negotiation was removed in favor of a single point format per curve. And the static RSA and Diffie-Hellman cipher suites were removed. Some other crypto that was removed, or crypto items: compression, since there had been some attacks on that in the past, custom DHE groups, and DSA. RSA padding was also changed to use the PSS scheme, which stands for probabilistic signature scheme. More of the handshake messages are encrypted in TLS 1.3. Here you can see a Wireshark capture of TLS 1.2 on the left side and TLS 1.3 on the right side. And you can see in TLS 1.2, things weren't encrypted until we got down to the finished message, which shows up here as encrypted handshake message. But in TLS 1.3, everything after the server hello is encrypted. So this means an attacker can see a lot fewer of the details that's going on in the handshake. There's a new 0 round trip time mode where application data can be sent upfront early along with the client hello. This does save 1 round trip for that first application data, and it's encrypted with a key that was derived in a previous session. There's a new encrypted extension, which allows extensions that were previously sent in the clear in the server hello to also be encrypted. even though the server hello itself is not encrypted. And so this is just an example of some of those extensions that you might see show up in the server hello. There were redesigned key derivation functions to allow easier analysis by cryptographers due to improved key separation properties. It uses a HKDF, which is an HMAC-based extract and expand key derivation function. Version negotiation was removed. TLS 1.2 and before included a version negotiation mechanism, and TLS 1.3 now kind of moves that into a version list, which shows up in an extension. This increases compatibility with servers that incorrectly implemented the previous older version negotiation. If we look at session resumption, now there's a single new pre-shared key exchange, which replaces the older session resumption, either using session IDs or session tickets of TLS 1.2 and earlier. This also replaces PSK-based cipher suites in earlier TLS versions. There is a legacy session ID field that was added to the client hello as part of middle box compatibility. There are some middle boxes that your traffic might go through in between your client and server that might still be expecting the session ID field to be there. And so that's what this field was added for. There's now 3 key exchange modes in TLS 1.3, DHE or ECDHE, PSK, or a combination of the two. And the full handshake now includes kind of 3 main phases, as you could think of them. So key exchange establishes the shared keying material, selects the cryptographic parameters, and everything after that's encrypted. There's the server parameters. This establishes some other handshake parameters like client authentication, ALPN. And then the third phase is authentication. This authenticates the server and or the client, provides key confirmation and handshake integrity. So if we look at the kind of the overview of the TLS 1.3 handshake broken down by those 3 sections, you can see the key exchange, the server parameters, and the authentication phase. If we start to look at those handshake messages, the client sends the client hello. That contains a random nonce, which is the client hello.random, a protocol version, which would show up as TLS 1.3 here, a list of symmetric cipher and HKDF hash pairs, a set of, and then one or the other or both of either a set of Diffie-Hellman key shares in a key share extension or a set of pre-shared key labels in a pre-shared key extension. It could also include some optional other extensions. So the server gets the client hello, processes that, and responds back with its own server hello message. It includes a couple things. If DHE or ECDHE is used, it contains a key share extension that has the server's ephemeral Diffie-Hellman share. If pre-shared keys are used, then it contains the pre-shared key extension, indicating which of the client's pre-shared keys was selected. And if both are used, then both are present. So the server then sends the encrypted extensions. This is in response to the client hello extensions. The server sends a certificate request message if it wants to do client authentication. Otherwise, that is omitted, just like previous versions of the protocol. The certificate message can be sent by either party. It contains the certificate of the endpoint. The certificate verify message is sent when the certificate is sent, which is a signature over the handshake using the private key that matches to the peer's public key in the certificate. Then the finished message is a MAC over the entire handshake. Like before, it provides key confirmation, binds the endpoint identity to the exchange keys, and in PSK mode authenticates the handshake. So one thing that could happen is an incorrect Diffie-Hellman, a DHE share. If the client doesn't provide a correct key share extension or something in the key share extension isn't supported by the server can reply back with a hello retry request that also contains the key share extension of what the server does support. And then the client can once again send its client hello back in a corrected manner. If there are no common parameters that are supported, the server can just abort the handshake. So there we see the client hello with a key share being presented, the hello retry request coming back with the key share of things the server supports, and the client can then send an updated key share message. There's a cookie extension, which has two purposes. The first is that it allows the server to force the client to essentially demonstrate it's reachable at the network address. The second is allowing the server to offload state to the client, so it can send the hello retry request without storing any state yet, where the client then has to respond back with another client hello. And so at that point, the TLS 1.3 handshake is complete, and the application can go on to exchange application data from there. There's a couple optimized variants of the TLS 1.3 handshake. There's a resumption with pre-shared keys, and then there's the zero RTT data mode. The first variant is the resumption and pre-shared keys. PSKs can be used to establish essentially a following connection. This is what was a TLS 1.2 and earlier called session resumption. So once the handshake is completed, the server can send the client a PSK identity corresponding to a key derived from the initial handshake, and then the client can then use that identity in future handshakes to negotiate use of that pre-shared key. If the server accepts the client's PSK that it presents, the security of that following context and connection is tied back to the original one. The key that was derived in the initial handshake is used to restart this the second handshake here. In TLS 1.2 and before, there were session IDs that were used, and we saw that show up in Wireshark, or session tickets could have been used. Both of these have kind of been deprecated now in TLS 1.3 in favor of using this pre-shared key resumption mode. So again, PSKs can be used with DHE or ECDHE. This provides forward secrecy in combination to using your shared keys. If you don't use DHE or ECDHE, the same key is going to be used for each connection, the PSK, and so there you'll lose the forward secrecy aspect of it. Here you can see the initial handshake happening, and after the finished messages get exchanged, the server sends back a new session ticket message. This is what's going to contain the PSK identity for the client to use for resumption in a following handshake. Here we can see the following handshake happening, where the client has then applied that pre-shared key information to its client hello. And if the server chooses to resume the session, it also attaches a pre-shared key extension to the server hello. Since we're using pre-shared keys and authenticating there in the resumed handshake state, we don't need to send the certificate and certificate verify messages again. The client does supply the key share extension when resuming PSK, as we saw in that first client hello message. The server does have the option to decline resumption and just fall back to a full handshake at that point. But if it does choose to resume, it can also send back the pre-shared key extension in the server hello message to essentially say that it's negotiating use of the previous pre-shared key. So the second handshake variant is the zero RTT data, or zero round trip time. So when this allows a client to send data on the first flight with the client hello, this data is called early data since it's upfront. The client uses the pre-shared key that it had acquired in a previous session to authenticate the server and encrypt this early data. If you don't do a previous connection, you can also pre-distribute the pre-shared key and obtain it externally. If you do pre-distribute the pre-shared key to your endpoints, you need to provide a few other bits of information to the client and server. You need to tell them what cipher suite will be used with that pre-shared key, the ALPN or application layer protocol negotiation that will be used if needed, and the SNI or server name indication if you need to use that. And with zero RTT, that early data is essentially just added to the existing one round trip handshake. It's just in the first flight. So it's a zero round trip to get that first early data over to the server. The rest of the handshake uses the same messages that we saw as the normal one round trip did, and then uses the PSK for resumption. So here we can see the client sending early data over, as in the form of application data here with the client hello. There's an early data extension, and then there's also an end of early data message that gets sent by the client. The RFC does call out the zero RTT variant handshakes are less secure. The security properties of the zero RTT data is weaker than those of other kinds of TLS data. And this is because that data is not forward secret. It's only encrypted under the keys that were derived from that pre-shared key. So if you send that data multiple times, it's going to be using the same key each time. The RFC also says that protocols that use TLS must not use zero RTT data without some kind of profile that defines its use. So what does TLS 1.3 mean for you? We covered these a little bit before lunch. It's, essentially faster in performance. We saw these slides before. More secure. It removed these algorithms and modes that are now legacy and not recommended. So what about using TLS 1.3 with wolfSSL? We do support the latest RFC now. We have supported several of the drafts along the way. I think we have one of the drafts remaining. You can optionally enable for backwards compatibility if you need, which I guess this slide calls out here. So to enable TLS 1.3 support, you use the --enable TLS 1.3 configure option. We have support for the older draft 18. If you need to be backwards compatible with some other implementations out there that only made it to that draft and haven't added support for the final yet, you can enable TLS 1.3 draft 18. You can easily use our client and server examples with TLS 1.3. If you remember, there was the -v option, which allows us to specify the protocol version. -v4 for our client and server indicate TLS 1.3. And then you can specify a TLS 1.3 cipher suite with the -l option. Of course, you can also connect our client out to external web servers and websites to test TLS 1.3. This is just an example of how you might do that connecting to Cloudflare. We support currently the following 5 cipher suites for TLS 1.3. So you can see there's no public key exchange algorithms shown in the cipher suite here, since those are now based on the certificate and keys that are being used. So it really shortens up the cipher suite list. So using TLS 1.3 from an application consuming wolfSSL, when you make your wolfSSL context, we have 2 new version methods, wolf TLS v13 server method and client method. If you need to use your own heap, we also have an extended versions of those that accept a heap pointer. There's a cookie extension, so this sends a cookie with the hello retry request to avoid storing state on the server side. If you want to use this with wolfSSL, you can use the --enable HRR cookie or define wolfSSL send HRR cookie. And then there's one API to call from your application, wolfSSL send HRR cookie that accepts a pointer to an SSL, a secret, and a secret size. If you don't, so in TLS 1.3, there'll be a session ticket with a PSK sent at the end that can be used for resumption. If you don't want our server to send that ticket, you can call one of these APIs to disable that functionality. If you want to disable Diffie element ephemeral or ECDHE key exchange modes from being able to be used in wolfSSL, you can do that by using one of these APIs at the session or context level. If you do call this, then you would just be using direct PSKs. One of the neat things in TLS 1.3 is there's a new key update handshake message. So in prior versions to TLS, to rekey, you'd have to shut down the session and reestablish it. In TLS 1.3, you can just send a key update message anytime after the handshake's been complete, and it'll cause a rekey procedure to happen between the client and server. Whenever you want that to happen after your handshake is finished, you can just call wolfSSL update keys with a pointer to your wolfSSL structure. Another unique thing about TLS 1.3 is that you can do authentication of the client and or server post handshake. So the client has an extension called post handshake auth, where the server, if that's available, the server can request client authentication anytime after the handshake's completed. It just sends another certificate request message, and the client would send back a certificate message. In order to enable this in wolfSSL, you have to use -- enable post auth or define wolfSSL post handshake authentication. And then you'd have to allow that explicitly by calling one of these APIs at runtime, either at the session level or the context level. Once it's enabled, you could request a certificate from the client by calling wolfSSL request certificate. You can request a certificate up to I think a maximum of 256 requests on a single connection. And then when we do the handshake, you can call the same wolfSSL connect and wolfSSL accept APIs to do the handshake like we saw before. If you want to be very explicit from your application and know that you're only doing TLS 1.3, we do have unique connect and accept APIs on the client and the server side. So on the client, you could call wolfSSL connect TLS v13. On the server side, you could call wolfSSL accept TLS v13. And once those finish, you've completed the handshake process if the return value is wolfSSL success. So looking at early data, these two APIs here allow you to set the maximum amount of early data that can be sent. If you set 0 size here, that indicates to wolfSSL that no early data can be sent. And you do have to enable early data support explicitly in wolfSSL with -- enable early data, or by defining wolfSSL _early_ data. If you do want to use early data, you can write that data on the client side by calling wolfSSL write early data. That'll do the handshake and send the early data internally. On the server side, when you're as an initial function call to in place of wolfSSL accept, you could call wolfSSL read early data, and that would start and continue the handshake on the server side, as well as receiving that early data that the client had sent. So that gives you a snapshot of our TLS 1.3 support. It's available in wolfSSL. We encourage you to try it out and use it. We see it being adopted more and more in the industry now than it was a couple of years ago. All right, next up. Next up is a few notes about using wolfSSL with non-blocking I/O. So you can use wolfSSL with I/O that's both blocking or non-blocking. Blocking is the default case, but there's a lot of use cases that have non-blocking I/O as well. In the blocking case, all the APIs that do call I/O will block along with that I/O. So things like wolfSSL connect, accept, read, write. If you call those, execution will just block inside of there down at the socket level or your transport level until data is able to be sent or received. Now, for non-blocking I/O, you can set your socket to be non-blocking, of course. This is at the application level, external to wolfSSL. And when you're using non-blocking I/O with wolfSSL, none of our I/O APIs will block anymore. So if the I/O application call that you're calling would have blocked, that API instead will just return SSL failure, which you might think is an error at first. But if you call wolfSSL get error, you're going to see the underlying error code is wolfSSL error want read or want write. And that'll tell your application to come back around and call that same API again with the same arguments. This is just saying that same thing. When you receive a want read or want write, the application should loop back around, call the same API again, when the IO is ready. If you don't want to call wolfSSL get error, we do have a couple explicit APIs. You can call wolfSSL want read or wolfSSL want write, and those will return 1 if the current error is that wolfSSL error want read or wolfSSL error want write. If it's not blocking and that error code is not underneath internal to wolfSSL, those will just return 0. If you enable debugging and look at your debug log, you'll see when the IO blocks and when wolfSSL detects that. You'll see a string that shows up that says embed receive error would block, or the inverse of that if it's the sending side. Usually you don't have to worry about this as long as your application is set up to properly loop around your higher level API. Our example client and server can use non-blocking sockets. If you use the -N option, then you'll see some output usually on the client or server side that says, client would block or server would block. And that's just an indication that the client application is looping back around then and trying to repeat that operation. In our wolfSSL examples repository, we also include a simple TLS example client and server that use non-blocking sockets. They're a little easier to look at and much smaller in size than our main example client and server are. So that gives you an insight into non-blocking IO. So nothing to worry about, just a few extra things to handle at your application layer if you are using IO that's blocking or non-blocking. Okay, so session resumption is up next. This is when you do one TLS connection, and then you want to resume that session in a future state. So why resume a session? It allows you to skip the performance expensive public key operations that happen in the handshake. It means the subsequent connection is going to have a faster connection time. There's a couple of ways that you can do this. This is TLS 1.2 and earlier. You can use a session ID. This is supported both on the client and server side. The server includes a session cache. Our default in wolfSSL is a default of 33 sessions, but you can adjust that cache at compile time. You can see the options we have available to you. You can disable it completely with no session cache. You can have a small session cache, which is only 6 sessions, a medium session cache, which has 1,055 sessions, a big session cache with 20,027 sessions, a huge session cache with 65,791 sessions, or what we call a Titan session cache, which handles just over 2 million sessions. Titan name coming from servers with titanic amounts of memory. For server-side support, you don't have to make any changes to your application code. You just have to have the session cache compiled in and set to your desired size. For client-side support, you do need to have a couple adjustments at the application level. After a successful connection, so say you call wolfSSL connect, that returns success. Maybe you do some reading and writing operations. You need to, if you're planning on doing session resumption, call wolfSSL get session, which returns a pointer to a wolfSSL session structure. And then later, when your application, after you get that initial session, you can close down the connection, free the wolfSSL session. After you're ready to do a resumption later in your application, after you call wolfSSL new and make a new wolfSSL session, you essentially store that saved session state back into the wolfSSL structure by calling wolfSSL set session. Then after you've reloaded that session state, you can complete the handshake like normal by calling wolfSSL connect. After the handshake is finished, if you want to know if the session was resumed or not, you can call wolfSSL session reused, and that'll return 1 if the session was resumed. Otherwise, it'll return 0. Using session IDs, you can tell if a client has resumed a session in Wireshark. if you look at the client hello, there's a session ID field there. If it's 0, that means it's a new session. If it's a non-zero session ID, that means the client's at least trying to do a session resumption. You could look in the server hello and see if the session ID is the same or different to tell, in Wireshark if that session has actually been resumed or not. So here are a couple snapshots of a Wireshark window. This is a client hello with a session ID length 0. So we know this is a new connection. Compared to this is a client hello with a non-zero session ID. So this is a session ID that had been assigned to the client in a previous session, and now it's attempting to resume that same session. Sessions do have a timeout value. The default for wolfSSL is 500 seconds. You can override this value if you need to at compile time by defining wolfSSL session timeout to a new value. When a session does timeout, the server essentially just falls back and does a new handshake in a new session. And this timeout value is really controlled by on the server side, since it's the one choosing if the session will be resumed or not. Some common issues with session resumption. If your client's not resuming, the session may have timed out on the server side and the server just decided it was going to do a full new handshake. If your session cache is too small on the server side, or maybe it's sized correctly, but you just had enough connections where the session cache entry for that old session was overwritten, that could cause the server to do a full handshake again. And another kind of outlier case, if the underlying PRNG is not being seeded by random entropy, say your generate seed call is returning a constant value, that can cause the server to give the same session ID to multiple clients. And so a client trying to resume with a session ID that doesn't match the keying material stored in that cache entry on the server is going to fail, and it'll probably fall back and do a full handshake. So the second way to resume sessions is with session tickets. This is defined in RFC 4507. And this is a way to resume sessions without the server having to save client-specific state. So it's useful if you have a server that's handling a large number of connections or transactions, and you don't want to have to use the extra memory of a larger session cache. Servers that want the sessions to have a longer lifetime can use a session ticket. If you want to be able to load balance requests across servers, not storing the state on the server allows a different server to easily pick up that session. Or if you're an embedded server and you don't have a lot of memory, maybe you want to just offload the session state and have the client handle it. So a session ticket is essentially a mechanism used to distribute encrypted session information, and it's in the form of what's called a ticket. The ticket's created by the server and sent to the client during the handshake process. Then the client can present the ticket to the server again to try to resume a session. The server stores its session state at the time of the first connection, such as things like the cipher suite, the master secret, into a ticket and encrypts that ticket with a key that only the server knows. Then the ticket's distributed to the client in the form of a new session ticket message. This happens as part of the handshake. When the client wants to resume the previous connection, it includes the ticket in the session ticket extension that attaches to the client hello message. So here we can see a first connection happening between a client and a server. The client hello just has an empty session ticket extension. The server hello, also just an empty session ticket extension, is going through the full handshake process. Once the finished message is sent back from the client, in response, before the change cipher spec message, the server sends back a new session ticket message, which includes that encrypted ticket. And then it goes through and finishes the handshake and proceeds down to application data flow. So here we can, if we look at Wireshark, we're looking at the client hello, we can see the session ticket extension. Here it's just a 0 empty session ticket, indicating this is just a first initial connection. Here's a server hello coming back. This is also just the first initial connection. We can see the session ticket message, indicating that it does support session tickets and that it'll be sending back a session ticket at the end of the handshake. Here's towards the end of the handshake, the server sends back the new session ticket message. We can see the session ticket is encapsulated in there. Here it's 142 bytes and has a lifetime of 300 seconds. So for client resumption, if the server does successfully verify the ticket the client presents, it can renew the ticket again and provide back another new session ticket message at the end of the handshake. If the server doesn't want to renew or honor the ticket, it can always just have the choice of falling back to a full handshake anytime it wants. So here is a client presenting a session ticket extension that has a valid ticket in it. Here's the server sending back an updated session ticket, new session ticket, handshake message that the client can use for a subsequent resumption again. And you can see the handshake's also abbreviated here. There's no certificate or certificate verify messages, for example. So to enable session tickets in wolfSSL, there's a --enable session ticket option. There's also some defines you can use if you're not using configure, have TLS extensions, and then have session ticket. The -d has TLS extensions is defining that just to enable general TLS extensions. You'd need that for any kind of TLS extension to be enabled in wolfSSL. So using session tickets from the application's perspective on the client side, first you want to enable them at runtime, either at the session level or the context level, using the wolfSSL use session ticket or CTX use session ticket APIs. You can get and set the session ticket using wolfSSL get session ticket and set session ticket. There's a session ticket callback. This is called when the session ticket is received by the server. It essentially gives you the byte array of the ticket with the corresponding size. That allows you to choose to write it out somewhere or do something special with it, depending on your application's use. To set that callback, you'd call wolfSSL set session ticket callback. On the server side, there's a callback to register for encrypting the session ticket. So to register this callback, you can call wolfSSL CTX set ticket inc callback, and then the callback is prototyped there at the first section of this slide here. On the server side, there's a hint which can be included in the new session ticket. It's a hint to the client of how long the ticket should be stored. And the client can either choose to use that or not, but it's what the server is recommending the client do. If the hint's set to 0, the lifetime is just unspecified. The client should delete the ticket when the time expires. And these terms are coming from the RFC as far as should and may. A client may delete the ticket earlier based on local policy, and the server may treat the ticket as valid for a shorter or longer period of time than what is stated in the hint. So it's more of a recommendation. As we saw in our TLS 1.3 deck, session tickets are now kind of the default thing that's used in TLS 1.3 for resumption, where session IDs have just been removed. So that gives you some insight into session resumption with wolfSSL. A number of our customers are cross-compiling wolfSSL for embedded targets. And so they have a particular tool chain that matches their embedded target, but they still want to use autoconf, to build wolfSSL. So a couple notes on doing that. wolfSSL definitely supports that. That happens all the time with our library. And you can use cross-compiling to compile wolfSSL on one system for a target system of another architecture or build. To do that using configure, you'll want to specify the host, so -- host equals, and this usually matches up to your toolchain naming as well. So here our host is ARM-Linux. Sometimes you also may need to specify the individual compiler, linker, etc. To configure, and there's a variable for each of those. So CC is the compiler, etc. LD would be the linker. Depending on your system and your tool chain, you might need to specify some other options, and you can pass those through to our cflags variable with configure. So here's just some examples of some things that you might need to set. Say you run an ARM device, where mCPU is the name of the ARM target processor, -m thumb compiles ARM thumb mode, -os is optimizing for size, and the specs rdimon.specs is enabling semi-hosting. If you want to control the installation location, you can use the -- prefix option, where you're just giving us a path to a location that will then install the library to, and you do a make install. Just one note, some versions of configure you'll see an error show up in relation to RPL malloc or RPL realloc. If you do see that show up, you can add these lines to your configure line, which we found in the past to solve that problem. And again, when you're cross-compiling, you're likely to have a lot of preprocessor defines to control the wolfSSL build. And here, just another reminder, we recommend using user settings.h with wolfSSL user settings defined, and then placing all your custom preprocessor defines into that file. Once you run configure, configure makes a make-file that you can use to compile the library for your target. Now, if you only want to compile the library proper, you can run make source/libwolfSSL.la. Otherwise, just running make by itself will try to compile our examples, our wolfgrip test, our benchmark, and our unit tests. And a lot of those things aren't quite as portable as our library proper is. By default, when you run make install, it's going to try to compile the entire library and examples first if they're not compiled yet, and then it's going to install the library and the header files and the other supporting files. If you just want to compile the library and the header files, you can run these two commands, which are a little bit non-standard in the form you might not find them in a standard autoconf documentation. So that's a couple tips on cross-compiling. Nothing too detailed, since at some point it kind of becomes dependent on the tool chain that you're using and the processor or platform that you're compiling to. All right, so up next is portability and customization of wolfSSL. We have a lot of areas inside the library that allow you to customize it for your specific platform use. In general, there's a lot of challenges, moving TLS to an embedded device. Some of those might be small memory usage, use on either small footprint size or small runtime memory use. It's not a desktop operating system, so there's a lot of different RTOSes, a lot of people just running on bare metal. So you have some things to think about there when you're porting code over to it. A lot of processors are just slow, where crypto is slow, especially some of the algorithms. A lot of the embedded devices don't have a file system. Some don't have logging capabilities if you're trying to enable debugging. And compilers vary from compiler to compiler, as well as standard libraries. So we try to do our best to make it easier for you to get wolfSSL products working on your target platform, even though they're varied. So for small memory sizes, you can exclude algorithms. So excluding just means compiling them out of the library completely. You can use a smaller algorithm. Some have a smaller footprint size than others. We have different math libraries, and controlling that can sometimes greatly impact the footprint size of the library. You can also use different key sizes depending on security levels and your requirements there. For lack of file systems and logging capabilities, we have some abstraction layers for both of those levels. You can disable file system use completely. We have a logging callback that you can use. For a slow processor speed, there, if you have hardware crypto available, that can sometimes alleviate your processor load sometimes and be faster running in hardware. You can also look at how algorithms perform comparatively to each other, and you might be able to choose an algorithm that's more performant. For different compilers and standard libraries, we try to do our best to build and test on a variety of compilers. And so just given the breadth of platforms that we have our customers running on, it's likely that we've already ported and got wolfSSL running on something similar, at least, to what you're going to run on. The slide's just saying, we've essentially designed wolfSSL with portability in mind. As far as design goals go, we know we're going to support a wide variety of operating systems and RTOSes. We know we want to support bare metal, just no operating system. We've done our best to integrate abstraction layers and callbacks when that makes sense. We support over 47 operating systems now, which is a long list, and that grows by at least a couple every year. We do support just running in a bare metal environment. So AutoConf, we've been using the configure, make install as we looked at wolfSSL. That makes it easy for Nix-like systems, Unix, Linux, Mac. And we've mentioned that we have project files that we try to include in the ID directory for other compilers and suites. As far as abstraction layers go, we've abstracted out the C standard library calls for memory, string handling, math, file system time. We've also abstracted out mutex locking, logging, custom IO, and some things about the operating system. So we're going to walk through those here to give you an idea of how you can, what we have available, and then how you can override that. So as far as the C standard library goes, this is going to be things like memory handlers, string functions, character handling, math functions, and file system. For memory handlers, most C programs are going to use malloc, realloc, and free. wolfSSL defaults to using those as well. I think most of our builds don't use realloc at all. We just try to use malloc and free since some embedded platforms don't have a realloc available. And we abstract the memory handlers internal to our code as xmalloc, xrealloc, and xfree. And so if you build wolfSSL, you define xmalloc user when compiling the library. You can then override these to your own memory handlers. So you would just define xmalloc, xrealloc, and free to your own custom malloc, custom realloc, and custom free. Everywhere internally to our library is going to call xmalloc when it wants to malloc memory, which will then end up calling down into your custom memory handler. And we have customers that do this if they have either different memory functions, they want to use different memory pools. Sometimes they even just want to handle their own static memory pool underneath our calls to xmalloc and xfree. If you don't want to do that at compile time, you can also register memory handlers at runtime by calling wolfSSL set allocators. And that just allows you to write a callback that will be called for malloc, free, and realloc. Those callbacks are prototyped in our wolfSSL wolfcrypt memory.h header with the following function signatures. So they essentially map mostly to what you would expect from malloc, free, realloc, but we also do have a heap pointer and a type that is a little bit unique as far as comparing to the system defaults. Those little bit unique arguments, the heap pointer is a heap hint for applications that want to use a custom heap. So if you remember, some of our extended functions took in a heap pointer that would essentially get passed back down to you at this level inside of your custom memory caller, your handler. And then the type variable in type is essentially giving you a hint to what type of memory is being asked for. So some examples are maybe it's just a temporary buffer if it's for allocating a SSL session structure or context structure, if it's an input buffer or an output buffer that we'll be using for reading in and out records. The next abstraction layer for C standard library is string functions. So wolfSSL does use string.h by default, using things like memcopy, memset, memcompare, and you can override these as well. We've extracted them out to x memcopy, x memset, etc. If you define string_user when compiling the library, you can just include your own header if needed, and then define these to your own custom memory string functions. Those are just an example. This is a full set of the ones that wolfSSL might call internally, and you have the opportunity or chance to override any of these at compile time. For character handling, wolfSSL uses the ctype.h header for functions similar to toUp or toLower in is alpha. We've abstracted these out as well, allowing you to override them. If you define ctype_user, you can map these by defining them to your own functions. For math functions, wolfgrip uses math.h. This is for things like pow and log, specifically used inside of Diffie-Hellman's dh.c. That'd be wolfgrip/source/dh.c. And wolfgrip calls xpow and xlog, so you can define xpow and xlog to your own functions as long as you build wolfSSL with user mathlib defined. For file system use, wolfSSL does use file system operations by default. We use them to read certificates and keys. And if you don't have a file system available on your platform, just build wolfSSL with no _file system defined, or I think we also have a disable file system enable option. Now, if you're going to disable the file system, you do need to adjust your application slightly in how you use files or buffers or C arrays. We saw before things like wolfSSL CTX load verify location is how you would load in a CA certificate into a wolfSSL context. You would need to switch that over to calling wolfSSL CTX load verify buffer. And we've got equivalent _buffer functions for most of the APIs that use files. For time, wolfSSL does require an accurate system time. We use time.h, and we use this for validating certificates and certificate chains in the not before, not after fields. We have a couple of different ways you can override time functionality, depending on what you've got available on your platform. Kind of the most liberal way is to define no ASN time. This just disables all time-specific parts of our ASN processing code. And this is only really used for systems that don't have a real-time clock. We don't recommend doing this if you can somehow get an accurate time value, just because it does then skip the date verification checks as part of the certificate validation. If you define user time, this will use wolfSSL's internal implementation of GM time and our internal time structs. And so here you only need to map X time, as we call it, to your own function that returns the seconds since the Unix epoch. So this is essentially the equivalent to just the normal time function. If you define time overrides, you're required to override both X time and XGM time. And so X time is, again, just a function that returns the seconds to the Unix, or since the Unix epoch. And XGM time is a function that converts a time T structure to a struct TM. So next category is threading and locking. By default, wolfSSL does use mutexes for locking. Some applications or platforms don't have locking support. And if that's the case, you can just build wolfSSL in single threaded mode. Note that if you do build in single threaded mode, the library won't be thread safe any longer. For logging, we talked about enabling and controlling debug logs by defining debug_wolfSSL or -- enable debug, and then either turning it on or off at runtime with wolfSSL debugging on or debugging off. By default, wolfSSL logs error or just log messages to standard error using fprintf. You can customize this in your application by setting a custom logging callback. So if you call wolfSSL set logging CB, you can pass it in a custom logging callback that's prototyped by the second code section here. When your logging callback is called, you'll essentially get a log level and then just the log message, or you can print or send that log message anywhere you'd like to. Our log levels can be found in wolfSSL wolfscript logging.h. You might want to put this, to standard out. You might want to put logging to a file. You might want to even just open up a socket and send it over a TCP socket. So it might be helpful if you don't have registering a callback. Might be helpful if you don't have standard error or an fprintf. Like I mentioned, if you want to push your log messages to a file, or if you don't have a file system or terminal, you can push them across an Ethernet connection over Wi-Fi or over a serial connection. So what about custom I/O? So we default in wolfSSL to using a BSD socket API, but we have a custom I/O abstraction layer available that you can use to write your own custom I/O callbacks and then send and receive data however you want. So this is meant for people who want to have a higher control over the I/O. You don't have a BSD socket available, or you just want to run TLS over something like an RS-232 serial line, Bluetooth, memory buffers, or something else. To use this, you'll want to compile wolfSSL with wolfSSL_user_IO defined. And then you need to essentially write or define two functions, the network send function and the network receive function. So these custom send and receive functions are prototyped in wolfSSL's, I think that's wolfio.h now. Here's the prototypes for each of those. Essentially your receive callback is going to be called whenever wolfSSL wants to receive data or needs to. wolfSSL will call your send callback whenever data needs to be sent. And we've already handled or will handle the encryption and TLS record processing. So your callback is literally just responsible for either, in the receive case, copying network data into that buffer up to a size that we request, or in the send case, just copying data in the buffer that we give you of size that we've told and just sending that across to your network stack. The callback functions need to be registered in the wolfSSL context using one of these two functions, either wolfSSL set IO receive or wolfSSL set IO send. There's an optional context per wolfSSL context that can be set. And essentially this is a void pointer that can be a pointer to anything that you want. If you call wolfSSL set IO read CTX or write CTX and pass that pointer in, you're essentially just going to get that pointer back out again in your callbacks. So you might need, to set that to a structure to access some part of your network or control how your data is being sent or received inside of the callback. Like I mentioned, the pointer to that custom context will be given back to you in your receive or send callback. As far as operating systems go, wolfSSL has already been ported to a number of different OSs and RTOSs, and you can look in our settings.h file, wolfSSL wolfscript settings.h, to see the list of those OS ports that we have. Typically, we've got one defined per OS or RTOS. So, free RTOS, safe RTOS, ThreadX, etc., where you would just need to define that or add that to your user settings and define it there. Same goes for TCP/IP stacks. We currently support LWIP. LWIP has both a BSD socket API as well as a native interface. We support NetX, and then a little bit newer stack called Pico TCP. All right, so some notes on some callbacks we have other than the ones we mentioned before. We have a handshake callback and a timeout callback. The handshake callback can be registered for wolfSSL connect and accept. It's useful for systems that you don't have a debugger available and you can't sniff the connection if you want to see what's happening in the handshake. if you define wolfSSL callbacks, it'll enable this layer. And then you'll essentially have access to an extended version of wolfSSL connector accept that accepts your custom handshake callback. And that handshake callback will be called with information about the handshake messages that are going back and forth. So it's giving you kind of the insight you would get in Wireshark or something like that, but packed inside of a little structure, and more minimal, of course, than all the details you see in Wireshark. The other timeout we have available is a timeout callback. It's defined as the prototype you see here. And it's essentially giving you a list of packets that caused a timeout to happen. So user settings, we've mentioned this a couple times. I think you guys are probably pretty familiar with how you register this, and you need to create your own custom user settings.h file. It allows probably the easiest path to upgrading from release to release of wolfSSL that you could have, as far as only maintaining one file from release to release. Again, just a note, if you want some example configurations, we've got some under the example/configs directory. You can use these with AutoConf if you want. We have a enable user settings configure option where you would do -- enable user settings. You might have to disable the examples since they might not build with depending on what options you have in your user settings. And then you could run make to compile the library. So we talked about portability and customization of wolfSSL. Next, we're going to talk about something fairly related, but how do you port wolfSSL to new platforms? There's a couple other things that didn't quite fit in that previous deck that you might want to keep in mind. So we talked about, wolfSSL tries to be as portable as possible. One of the things that we produce is what we call the wolfSSL porting guide. And these are essentially the steps we use internally that, when we are porting wolfSSL to a new platform, and that you can follow along in this guide when porting to a new platform or your own platform. It's not always a new platform, it just could be, a non-AutoConf type system. So this was in chapter 2 of the wolfSSL, or I should say chapter 2 of the manual explains how to compile wolfSSL. But a lot of that focuses on, compiling with AutoConf, and sometimes it's a little less clear how to compile with the embedded target. We mentioned that in settings.h, we have some defines for existing port layers. And so that's the first place to start before you go, making adjustments for your own new port. So the two main locations you can put defines, when compiling and porting wolfSSL would either be in user settings.h, which would be the preferred, or you could also adjust settings.h, by say uncommenting one of our existing defines in there. But if say we have a define for RTOS in settings.h, you can, if you just want to leave that commented out in settings.h, you can go ahead and put that in user settings, and that'll work just fine. So we talked about user settings a couple times now. In general, we do encourage submission of patches and code changes. So if you end up getting wolfSSL running on a different set of combinations as far as platforms or OSs or RTOSs go, feel free to submit it back to us as a pull request on GitHub, and we'd be glad to review it and give you any feedback, and ideally accept it into wolfSSL master, which would go out in future versions. That just makes it easier for everybody to maintain, since we can maintain that port for you internally, and then you don't have to apply patches on your end as you update between versions. To accept code back from external contributors, we do have a contributor agreement that does need to get signed. That's usually a pretty easy process and just a couple page document to read through and sign. If you want to submit your changes on GitHub, that's usually our preferred way, just because then we have a nice seamless tool and platform to do reviews on that pull request. But if you don't want to be, if you don't want to have your code public, feel free to email us directly at facts@wolfssl.com, and we can do the review offline. So the first thing you'll want to look at when porting wolfSSL is data types. wolfSSL does benefit size-wise from having a 64-bit type available. And we have two defines we call that are size of long and size of long. And what those should be set to is this essentially the return of size of long and the size of long output on your target platform. And we'll use those internally to set some of our own internal data type sizes. So here's an example of if you added a new define for your platform called my new platform. Inside of that, you define size of long and size of long. Typically, that's going to be 4 and 8. We use two additional types that we call word32 and word16. Word32 would map to a 32-bit type and word16 would map to a 16-bit type. If our default mappings are different than what you require on your platform, you can change them by defining wolfSSL types and then adding your own type defs in user settings.h. So this is what our code looks like internally. So unless you define wolfSSL types, we're going to define word16 to an unsigned short and word32 to an unsigned int. We also have a byte type that we define or type def to an unsigned char. One of our math libraries called fastmath uses a FP digit and FP word type. These are mapped in our wolfSSL wolfcrypt tpm.h, and the value of these does change depending on your build configurations. If you need to override these, you can define wolfSSL big int types in your user settings.h. I would say most people typically don't need to override those, but it's there as an option for you if you do need to. So endianness, when is this important? This is important if your platform is a big endian system, because wolfSSL's default configuration defaults to assume a little endian system. So it's a quick fix. If you're on a big endian system, you define big _endian_order. So there's an example of defining that inside of your own My New Platform section. Write v, when is this important? If you don't have sys uio.h available on your platform, there's a couple places that wolfSSL does use write ev semantics. And if you don't have that header available, you essentially can just compile out those areas of code by defining no_write v. For input and output, we talked about how you can write and register your own IO callbacks. So this section is kind of re-explaining that. If you don't have a BSD socket API or you want to use a custom transport layer, you can define wolfSSL user IO, write and register your own IO callbacks. If you want to use our default IO callbacks as a reference to write your own, that's not a bad idea. You can find those in wolfio.c, I believe. They're called embed send and embed receive. And you'll see in our default case, they're just going to call down to the normal TCP socket functions. wolfSSL does use dynamic buffers for IO by default. So we'll default the first initial size of those to 5 bytes. Then as we read in a record header, look at the length, we'll dynamically grow and shrink that buffer as needed. TLS records can grow up to a maximum of 16 kilobytes each, which is 2 to the 14. And that's just defined in the specification as the maximum TLS record size. You can lower this in a couple ways. So if you control both client and server, you could explicitly reduce the size of this. But most of the times you're only going to be controlling one side of the connection. And if that's the case, you can try to use the TLS maximum fragment length extension. This is a client hello extension where the client can request from the server to use a lower maximum fragment length size. The downside here is that the client doesn't necessarily need to go ahead and follow that request. It can choose not to, or if it doesn't support that extension, it's just going to ignore it. If you prefer instead to use a large 16 kilobyte static buffer instead of growing and shrinking dynamic ones, you can define large static buffers when compiling our library. If you're using dynamic buffers and wolfSSL write is bigger than the buffer size, essentially a dynamic block will be used up to max record size. If you do really only want to send a block of the current buffer size, which is record size, you can define static chunks only, and then the record size defaults to 128 bytes, which will be sent. For file system, we talked about this. You'll want to be concerned here if you don't have a file system, if your file system functions are different than our defaults or not available. We use file system for loading key certs, CRLs, Diffie-Hellman parameters into the TLS session and context. And like we talked about in the past, we do have a lot of buffer functions which allow you to use memory buffers instead of your file system. You can disable our file system use by defining no_file system and then fall back and use our buffer APIs. This is just an example of defining no file system in your new platform section. If you remember, we looked inside of wolfSSL, we had a certs directory, and we ship a lot of test certificates and keys with the library for prototyping and getting up and running. We also have tests, key and certificate memory buffers available too. So inside of the wolfSSL/certs_test.h header, we have 1024-bit RSA keys and certs if you define use cert buffers 1024. We have 2048-bit RSA keys and certs if you define use cert buffers 2048. And then we have ECC NISP 256 keys and certs if you define use cert buffers 256. You can also use that gen certbuff.pl Perl script or the dir to c.pl script to convert your own files to memory buffers or C arrays. So we have a file system abstraction layer if you do have a file system, but it's different than the ones we currently support. We do have some other ports available. So, for example, on Freescale MQX or NXP now, MQX, it has its own file system functions. We've already integrated that file system in, and it just kind of defaults to those when you define Freescale MQX. But if we still don't support your file system, we've abstracted our file calls to X, etceteras, Xfile, XFOpen, XFSeek. And inside of your custom port block, you can essentially define these to your own file system calls. This is just an example I took out of our code for our Micrium port, where their file system functions are named a little bit differently than your standard file systems calls would be. So what about threading? When is this important? This is important when you want to use wolfSSL in a threaded environment or a single threaded environment. If you don't have threading available and you want to disable wolfSSL's use of threading in mutexes, we do have some existing ports of threading layers available on different platforms already. But if you want to just completely disable our threading support, you can define single threaded when building the library. You can also, if you do have mutex locking available, you can also port our mutex layer over to match your needs. If you look in wolfSSL wolfgrip/wcport.h and wolfgrip/source-wcport.c, you'll find our existing mutex layers. We have a function called wolfSSL mutex, which will need to be defined for a new platform. And then a couple additional functions called init mutex and free mutex. I think there's a couple that follow that same pattern. What about random entropy? So when is this important? We default to using dev random or dev urandom to get CDA or PRNG with random entropy. If those aren't available, this is something you need to think about. If you want to integrate into a hardware-based TRNG, or if you just want to use a different source of entropy than dev random or dev urandom. So you can disable our default seed generation code if you define no_dev_random. In that case, you'll need to write your own generate seed function in random.seed that calls down and gets entropy from somewhere else on your system. Or like we talked about before, you can define, one of these three defines to customize how the entropy is acquired by wolf script. So custom ran generate block. uses the specified function that this is defined to as the PRNG and skips our internal one. Custom ran generates seed, uses the defined function to get seed values. And then custom ran generate seed OS is the same as the above, but you also get the added OS seed parameter in case you need to get some extra info from your system. What about for memory use? This is important if standard memory functions aren't available. You want to use different memory handlers, or you're interested in memory usage differences between different math libraries that we have underneath wolfcrypt. By default, we'll use, like I said, malloc, freealloc, and free. If you define xmalloc user, then like we talked about before, you can override xmalloc, xfreealloc, and xfree. We've got a couple different math library choices underneath wolfcrypt. We have a normal big integer library. So this was our first library. It uses more heap, less stack. It's no longer enabled by default. This slide is outdated. We've since switched our default to be spmath, which is our newest math library. Fastmath uses more stack and less heap. It's more performant than our older normal big integer library. And it's enabled by defining use_fast_math. spmath, this is our newest math library. It was designed to be designed from the ground up to be timing resistant. So we wrote all of the code inside of our spmath library. And it's got some really nice assembly optimizations for a good number of platforms now. So it's probably the most performant in a lot of cases. If you're using fastmath, you can reduce stack usage using a couple defines: TFM timing resistant, ECC timing resistant, and alt ECC size. This slide I think is a little outdated, and we have a deck on memory usage, which we're actually going to look at next. So I'm going to skip over this section. We talked about time handling, where you can override our time and GM time functions by defining xtime and xgm time. If you define user time, you can define these three things to your own implementations. wolfSSL itself uses the time function for a clock tick function. In our source internal.c file, we have a low-res timer, which is used for expiration of session caches. And this is where you'd need to have essentially a function if you didn't have time available that provided it kind of an incrementing seconds counter. It doesn't need to be correlated to the epoch. It just needs to have second accuracy. And if you want to override this, you would need to define user_ticks. We talked about the C standard library already, so I'm going to kind of skip over this section. We also talked about logging a couple different times. For public key operations, by default, we're going to use wolfcrypt's implementations or the associated hardware crypto that is available and enabled. We do have some different callbacks you can use if you want to override some of these operations. So we have essentially sign and verify and then encrypt and decrypt callbacks for ECC and RSA, where when wolfSSL does one of these operations, it will call the callback, and then you can do that operation however you choose. For atomic record layer processing, this is when you want to override the MAC and encrypt and then decrypt verify operations that wolfSSL is doing. By default, we'll handle all those operations for you. We do have some users that want more control over that, and they want to override it and call into their own library or their own hardware to do that operation. Here, there's a couple callbacks available to you, one for MAC generation and encryption, and then one for decryption and verification of a MAC. When you're porting, you can also customize the features of the library. You can enable and disable features to try to either reach your desired algorithm and feature set or try to customize down the footprint size. The first thing we recommend doing when you're porting to a new platform is running the wolfcrypt test. So get the test.c running on your environment. This verifies all the crypto is working correctly and that you've done all your porting correctly, at least at the crypto level. And then the benchmark application is a nice one to have there available as well, just to make sure you don't see any kind of performance oddities show up after you've ported. It's also, pretty helpful if you're using some of those sections that allow you to customize the algorithm control. And then as a last step, you can get our example client server, or just a simple example client server running on your platform. That'll verify the TLS SSL layer is working correctly. Okay, so now that we've talked about porting wolfSSL, I mentioned we had some updated memory use and tuning guidance. So the memory use of wolfSSL and wolfgroup can really vary. It changes depending on which of those math libraries you have available and enabled, which algorithm you're using in Cipher Suite, what key sizes you're using, how you've customized the library, what optimizations you have turned on at your compiler level, and then if you have debug symbols and debug logging enabled or not. In general, wolfSSL is typically going to be between 1 and 36 kilobytes of dynamic memory per TLS session. A lot of this comes from the dynamic 16 kilobyte buffers that are needed for the maximum record size in TLS. This maximum record size is defined by the RFC to 2 to the 14 bytes. There's also a little bit of overhead on top of that. We mentioned there's a couple ways you can reduce this. If you control both sides, you can lower it down manually, or you can try to use the TLS maximum fragment length extension if supported on your server side. So these are some comparisons we ran recently, which are kind of interesting to look at. This doesn't give you hard numbers, but it's a relative footprint size between some of our different builds. You can see the builds on the first column, the library footprint size in comparison in the second column. This is going essentially from smallest footprint to largest footprint across a couple of our different math libraries, that being specifically our fast math library, which is tfm.c, or our SP math library, which is spint.c. So you can see the smallest footprint library is using our SP math all in its small configuration. The largest footprint library, which is probably also going to be one of the most performant, is using fast math with our SP enabled and our SP assembly support. This second slide here, this is average connection times. Again, not using specific numbers, but relative to each other. The faster the connection time, the higher in the chart. So at the top, you have the fastest connection. At the bottom, you have the slowest. So you can see that using our SP math library is going to give you the fastest performance. As you go down, using heap math, which is our integer.c, kind of the oldest math library we have, is the slowest. And so there's a lot of different permutations you can do here in the math library and configuring, with different sizes and assembly on or off between the 3 different math libraries. This slide is going to look at stack use during the TLS handshake. So this shows the first couple columns here are for TLS 1.2. I guess columns 3 and 4, and then columns 5 and 6 are for TLS 1.3. At the top, we've sorted here by less stack use first, and then increasing stack use generally towards the bottom. So if you're going for smallest stack, it would be our SP math library, which is going to give you the numbers at the top. And then along with that, that previous one was stack use. This is heap use during the handshake. Again, columns 3 and 4 are TLS 1.2, 5 and 6 are 1.3. Less, and this is sorted going from smallest heap use to largest heap use at the bottom. The smallest heap use is again going to be our SP math library. A couple notes are we try to keep our wolfSSL structure around 1K. We also do try to free up handshake resources after the handshake is completed. So, dynamic memory is going to go down after your handshake is finished. One easier way to control some of the RAM use is by reducing the session cache, and some of that might actually be controlling more of your footprint space. But we've talked about how you can control the size of the session cache based on the number of sessions that it will be storing. For our fast math library, there's some tuning you can do here. FP max bits is in relation to public key operations that the math library handles. So this should be set to twice your maximum key size that you want to handle. So if you want to handle 2048-bit RSA keys, you should define this to 4096. If you want to handle 256-bit ECC keys, you should set this to 512. For sizes that aren't multiples of 32, you can use the general rule of the key size times 2 plus the size of a digit bit, which is typically 32. TFM timing resistant will help reduce the stack usage. It also makes the Tom's fast math library, it enables some timing resistant code there. ECC timing resistant does the same and also reduces the heap usage slightly. It's going to be a little bit slower with some of the added timing resistance that it adds in there. Alt ECC size is a define that's helpful if you have both RSA and ECC enabled. It can help reduce some of the math buffers in the structures around where we use ECC. FP ECC, this is a fixed point cache for ECC operations. This will speed up repeated operations that are using the same private key. And really only repeated operations, your initial operations, you'll see, have not much of an impact on. FastMath does have some assembly optimizations available for different platforms. You can see the list here kind of reflects the architecture that's available, and you would just want to define one of these to enable those assembly optimizations. For stack usage, some of our users want to use the least stack possible and push everything else to the heap. And so if you enable our small stack build, which has a configure option or a define, our goal here is to use at most 1 kilobyte of stack. And so if we use more than that, we try to push everything else to the heap dynamically. Part of stack usage, we have an enable stack size option, where our example client and server will then print out it will print out the stack used by those examples. You can see here on the left is the server running and the right is the client running. And at the bottom, it prints out stack used. That'll change depending on the system you're running on. Sometimes types and structures can be larger if you're just on a standard desktop or server system. For verbose stack tracking, you can do enable stack size equals verbose. Running the wolf curve test then will print out relative stack usage for each algorithm. For heap usage, we have a couple options. We have use wolfSSL memory and wolfSSL track memory, which enables memory tracking of the dynamic memory. If you do -- enable track memory, the examples will print as kind of a summary of your dynamic memory use at the end. So total ALEX, DLX, bytes used, peak bytes, and then current bytes, which should be 0 by that time. We have a verbose heap tracking that also is enabled with the enable track memory equals verbose. When using this, the wolf curve test is going to print high watermarks for heap use per algorithm. If you're trying to optimize for footprint size, almost all of our algorithms can be disabled. So if you don't need a certain algorithm, you can disable it. It'll take that out of the final library size. If you can use hardware crypto, that's going to help reduce down your footprint size. One of the larger ones there is AES. They have a set of tables that use around 10 kilobytes. So if you have our hardware crypto enabled, that's going to, compile out the 10K there, or that'll be done in your hardware instead. You can also help reduce the size by using any optimizations that your compiler has available for size. Some notes on general tuning. We have a no inline define. This will disable inlining of some of our functions. It's going to be slower, but about a kilobyte smaller. We have a bench embedded define. This is going to reduce the memory usage of the wolfCrypt test and benchmark apps. You'll probably need to use that if you're going to try to run those on an embedded target. We talked about wolfSSL user settings, which is recommended. Just kind of a summary of the memory use enable options. So enable track memory, it'll define wolfSSL track memory and use wolfSSL memory. wolfSSL init and wolfCrypt init will initialize the tracking code internally. And then wolfSSL cleanup and wolfCrypt cleanup will automatically print the memory use using printf. Enable track memory equals verbose will also define the additional wolfSSL track memory verbose define. And it'll expose a couple APIs from our wcport.h function that allow you to view the peak allocation and peak bytes at that point. So what about algorithm-specific tuning? So these are all things that you kind of methodically go through with wolfSSL and wolfCrypt as you're kind of optimizing it down to meet either your footprint or memory size or either just your algorithm requirements. For AES, we've got a couple controls here. For AES GCM, you have 4 different options. A small option of word32, a table, and a table 4-bit. They have size and speed trade-offs, which I think we have a comparison here coming up. If you just want to disable AES altogether, you could define no AES. So I mentioned the 4 different AES GCM build options. This is a performance comparison we captured on an Intel Core i7. You can see from left to right, you've got GCM small, word32, table, and table 4-bit. And that's the order that they progress in performance. So higher the better numbers here. So GCM table 4-bit is our most performant GCM implementation or tuning option. This is the same performance comparison, but this is on an ARM Cortex A8, which is ARM v7. So you're seeing the same relative performance comparison, just giving you a little insight onto what it looks like on a more embedded target. So here's a comparison between our AES GCM options that show you stack usage and footprint size in addition to performance. So you can see that GCM table 4-bit was our fastest, but it's not necessarily the smallest if you're concerned about your resource use or stack use. So there's not really always a best option. It kind of depends on your requirements and what you look like as far as available memory goes on your system. For SHA-1, we have a use slow SHA defined, which is about a K smaller, but also about 25% slower. If you want to disable SHA, you can do that by defining no SHA. For SHA-2, we have a use slow SHA-2. It's about twice as small, but 50% slower. And you can also disable SHA-256 by defining no SHA-256. For RSA, we have a RSA low mem defined. It's going to use half as much memory, but also be twice as slow. And then if you don't need RSA, you can disable it by defining no RSA. For ECC, you can save some footprint size by manually enabling just the curves you need. If you define ECC user curves, then you have to define per curve you want enabled. So if you wanted, ECC 192-bit support, you could define have ECC 192. ECC Shamir, this doubles the heap usage, but gets a little bit faster. It also increases your footprint size by about 3K. It's an optional ECC calculation method. If using fast math for ECC, there's a couple ECC specific optimizations per key size. So you would just define the TFM ECC option specific to the key size you're looking for. For curve 25519 and ed 25519, you've got curved 25519 small, which optionally uses a small math implementation, uses less flash usage, but also slower. Some other resources we have available, we have a tuning guide with a couple more notes. You can reference our wolfSSL manual, and we also have the wolfSSL resource use document that outlines some memory use across math libraries. So that gives you a summary of our memory use and some tips on tuning. Hopefully those will come in helpful if you're trying to optimize down footprint size or control your runtime memory. So one of our newest math library and one of our currently supported math libraries is called SP, or Single Precision. This slide deck in this session is going to go through some details about this and why this is more beneficial to some of our older libraries, and how you can control this library as far as configuration goes. So why did we need another math library? We wanted something that was really fast and something we could easily optimize and add assembly optimizations to. Ideally, we want to be at least the same speed as OpenSSL. Ideally, in the ideal case, we can even be a little bit faster in some cases. We wanted an easier way to implement assembly code for all operations. We wanted this library to be secure from side channel attacks. Some of our older libraries, we had to keep patching here and there, for timing resistant areas that we discovered as researchers or testing exposed them. But this one, we wanted a math library that was just written from the ground up to be side channel attack safe. And then we wanted to be able to generate algorithm code based on algorithms. So we have some scripts that generate a lot of this library code for us. So just to kind of reiterate our current library support, we have our normal big integer library, which is located in integer.c. If you disable fast math, you're going to be using integer.c. This was written to be simple and have a small code size, use small amounts of memory. It uses a lot of dynamic memory, so dynamically resizes memory as needed. It's good for some embedded applications, but typically we see people migrating towards one of our newer math libraries. It's not really suitable for applications where you can't use any dynamic memory. A lot of safety critical applications prohibit that, unless you're going to implement your own static memory allocator and override xmalloc, xfree, etc. It's also not hardened against side channel attacks. So the TFM library is the fast math library. You can enable this with enable fast math, or optionally, we have enable fast huge math option. Use fast math is the define that corresponds to enable fast math, and this is going to be located in tfm.c. Originally, this was based on a larger public domain math library called Tom's Fast Math. And so we took that internal to wolfcrypt and have made a lot of changes to that since originally adopting it. The code here was written to be fast. It's definitely more complicated and larger in size than the original big integer library. It has a lot of case-specific implementations for different assembly areas or different areas of the math. The size of a data number is fixed, so it does reduce the dynamic memory reallocations a lot. It is hardened against side channel attacks using our TFM timing resistant define. So in general, it's going to be suitable for more people than the first normal big integer library was. Our newest library, SP Math All, this is enabled by enable SP Math All and located in spint.c. We try to make this kind of the best of both worlds. It's able to be small or fast depending on configuration. It's written from scratch and maintained by us. It can be compiled smaller or faster than either of the previous libraries. You can either compile it to be small and fast or very fast and huge. The size of data number is fixed here, so it doesn't have any dynamic reallocations. So it's much easier to use in safety critical type applications. It has a lot of assembly code in it now, so you can see the list here towards the bottom. A number of different architectures are supported out of the box. It's also just been written from the ground up to be kind of hardened against side channels by default. So here's a summary comparison between the three math libraries. Number data is dynamic in our integer library fixed in the TFM and math and SP math all libraries. Memory usage is small with the integer library, large or huge with TFM, and can be anywhere from small to large to huge with SP math all. Speed, integer library is the slowest. TFM can be fast or very fast. And SP math is, again, slow to very fast, depending on configuration. Assembly code, integer math doesn't have any assembly. Up to SP math all has lots of assembly. And then the only implementations hardened against side channel attacks are TFM and SP math all. So the available SP math all build options, you have the default, you have an equals small, equals huge, or you can individually select based on the key size. This is a performance comparison of SP math all, the small variant, versus our normal big integer library. So you can see they have RSA, DH, ECC operations on x86 and AR64. So across the board, ECC is consistently faster, about 50% on x86 and 100% on AR64. RSA and Diffie-Hellman are a little variable. If you look at code size, again, this is on ARM Cortex M4, integer library, SP math all. SP math all is going to be 13 to 25% smaller. Now, if you look at the huge configuration of SP math all, so the footprint size is going to be a lot bigger. This is in comparison to our TFM performance, since that library is going to be more performant anyway than big integer. This is percentage faster here. So, you know, in all cases, the SP math huge is faster. It just varies depending on operation. You know, Diffie-Hellman key generation is, or key agreement maybe is the lowest. On x86 is 6% faster. But it ranges up to, you know, some of the larger ones, ECC P256 agree or sign time is, you know, 50+% faster. Looking at the code size between SP math all, huge, and TFM, here you can see we're significantly smaller in code size than the TFM library is, on the order of, you know, 71 to 70, almost 74% smaller. Here's our SPM math all library built in small configuration with a no assembly in comparison to OpenSSL with no assembly. We're faster across the board, you know, for RSA and ECC, anywhere from 8 to almost 30% faster. So that wraps up our SP math library section. Let's see, I think we might just want to open it up to questions, since we've got about 9 minutes, you know, until our 3 p.m. Pacific time. But let's see if anybody has any questions here first. Okay, looks like no major questions. Yeah, and you're welcome. I'm happy to present these things to you. Since we've got a couple minutes left, I think I'm going to skip over and go through we have a quick slide deck on our vulnerability management process, just to give you some insight into how we work internally around vulnerabilities. So of course, you know, we take all vulnerabilities seriously, and we want to, of course, reduce the vulnerabilities that do make it out into our end product, which is why we put a lot of effort into testing up front. But when we do have vulnerabilities reported, we try to take that seriously and get fixes in place and a release out. Our mean time to verification of a vulnerability that's reported to us is about 1.5 hours, with our mean time to fix being about 12 hours. Resolution time depends on how complex the vulnerability is, but Typically, we're able to have a resolution time somewhere between, a half hour and 24 hours. Over the last 3 years, the mean time between a report that's sent to us and a release is around 38 hours, which, we think that's doing pretty great. So what does the process look like internally when a vulnerability gets submitted to us? The first thing that happens, this is in, anywhere from 45 minutes to a couple hours. Our support staff receives the vulnerability report, deprioritizes all other support to confirm the vulnerability exists. If the support staff needs to make any changes to the test code in order to get it to build out of the box, they go ahead and do that at that point. The support staff will also create a little README that we can bundle up with the reproducer, and then that's all sent over to the engineering team to hopefully be able to reproduce the issue in less than 10 minutes. As soon as the validation, the reproducer, and the documentation is streamlined up, that's sent over to engineering along with the original report. The second thing that happens, this can happen anywhere from 20 minutes to a day. Our engineering team will fix the issue, open a pull request on our GitHub repository, and then we'll have a couple different of our engineers review the fix depending on what area of the code it was in. The third thing that'll happen, this typically is about an hour out. We'll start our automated Jenkins tests on the fix. This will, test everything from build options, Valgrind, to test memory leaks, static analysis, and also some fuzz testing. The fourth thing that happens about an hour out is we'll have one of our senior engineers review the Jenkins results and the suggested fix that our assigned engineer has put up. The fifth thing that'll happen, which really isn't time, is that we'll just repeat steps 2 through 4 as necessary, based on either feedback or based on the Jenkins test results, creating fix, submitting a pull request, and having a senior engineer review the fix. The sixth thing that'll happen, the fix is merged into master, our GitHub branch. That's what we use as a basis for all of our releases. So the seventh thing that leads to is, can be about a day out as a release process is started. We'll post a new GPL release to the website and then regenerate and send out commercial releases to customers. So overall, we strive to keep our vulnerabilities low through testing. We take our vulnerabilities seriously, and we do try to be as responsive and reactive to all reports as we can.